Okay, we'll start from current slide, and I'll even turn on the projector. Okay. Now, technically, Tuesday is the last day of class, okay? And Thursday is technically when your final is. Okay. We have done everything in chapters 1, 2, 3, 4, 6. The labs. The test for chapter 6 is today, the last 30 minutes today, from 7:15 to 7:45, depending on how things are with chapter 8. So all we got to do today is chapter 8. If we finish chapter 8 early, we can do you can take the test early. Now, if we finish as early as 2 hours, which I don't think we're going to do, but if we were, then we can do the lab for chapter 8 and then take the test for chapter 6. Okay? Don't think that's going to happen. Okay? So I think it'll take us more than 2 hours to finish chapter 8. And then, after we finish that, we'll have the test for chapter 6. If we don't finish 8 today, then we'll finish it on Tuesday for sure, have the lab on Tuesday for sure, and then it'll be completely up to you whether you take the test for chapter 8 Tuesday or wait till Thursday. If we're just finishing the chapter on 8, I hate to test you on it before you've had a chance to study and go back and review all that. But I think we may finish 8 today. We'll see. Now, if that goes according to plan, that we finish 8, then have the test on 6, then all that we have to do for Tuesday is the lab for 8 and then the test for 8. Now, if any of you opt to, and this is completely up to you, take the final early, you can, if there's an opportunity to. Okay, Taylor just came in. Mac just came in. And is that all? Yeah. Just 2 came in? Okay. All right. Now, therefore, because some people haven't gotten everything in there or finished taking all the makeup work, I won't be returning papers to you. Well, let me start with this. I've received 2 and only 2 research papers so far. Okay? Please get those in. Please, hurry, as soon as you can. Tuesday is the last day. After Tuesday.
You received mine, right?
Okay, did you email it?
Yes.
Okay, I may have received it, but I haven't graded it yet. Okay, I've graded 2 is what I was saying. Okay, good deal. Thank you. All right. I correct that. 3. I've gotten 3 yet. Okay. That I've graded. Okay. Lab 1. Still have 1 person, and he's not here. That's 2 people. One of them is here, who hasn't turned in lab 1. Okay? Test 1. Test 1. I do believe everybody's done test 1. Is that correct? Anyone here who has not done test 1? I can unload test 1. Finally. Wow. Yeah. I'm going to pause recording for now. All right. So what we'll do is, I didn't put all that on the recording, so let's make a summary on that then. Okay, today, hopefully we'll get most of chapter 8 done. Maybe all of it. If we finish chapter 8 before 7:15, then we'll start the test on chapter 6. If we don't finish chapter 8 before 7:15, we'll stop there.
7:15 or 5:15?
7:15. Because we don't have a lab today.
Oh.
Yeah, there's no lab today. Now, if we finish by 5:15, which I don't think we will, then we'll have the lab on chapter 8. But I don't think we're going to get there, especially at the rate we're going now. Okay? So, if we finish chapter 8 before 7:15, then you can have your chapter 6 test then and leave when you're through. If we don't finish chapter 8 by 7:15, we'll stop at 7:15 and you'll take your test and go when you are through. Okay. If we do finish chapter 8 today, which I think we have a shot for it, then Tuesday will be pizza. I'll be passing out labs and tests. And by the way, if you haven't finished everything by then, it's going to be too late. So you have today, you have tomorrow. I'll be here 8 to 12. And by the way, I'm not going to the Birmingham campus on Friday anymore because the B building, as far as I know, is still closed. Okay? So I don't have an office over there anymore. The office is there, but I can't get to it. Okay? So I'll be here tomorrow from 8 till 12. And Monday, let me tell you this. Monday, I'll be in the office by 8, approximately. However, at 8:30, I'll be in this classroom having a review session with one of my classes. Okay? That'll go from 8:30 until 10:20. Okay? So I'm out of pocket completely from 8:30 till 10:20. But after that, from 10:20 on, I'll either be here in this classroom, my office, which is 265, or some room in between. Because if I have students coming in to make up a test or to take one early or something like that, I'll find the closest classroom to my office, which is 265, up to this classroom. Okay? I know this one will be available. And so I'll be somewhere between 265 and 255 after 10:20 on Monday. Have no more finals the rest of that day. But on Tuesday, I have a final in 205. And that's from 8:30 in the morning until 10:20. So I'll be there from 8:30 till 10:20, 205. If you want to come in there to submit something or other things, you can bring it to me there. And except for those, I'll be there the rest of the week and all week, except for this class. This class I'll be here at 3:15. We'll have pizza. I'll pass out all your things. So that's what I'm saying. Get to me all your late work before 3:15 on Tuesday. Okay? Then after that, basically the rest of the week, I'm somewhere in between my office 265 and this room 255 for the rest of the week. Now, if you should bring something by and you cannot find me, I may be in the registrar's office or somewhere having to take care of a student registering or something like that, then just slide it under my door. Okay? That'll be perfectly fine. 265. Not this door. 265. My office door. Any questions? Yes?
I can take my final Thursday of next week.
Yes, the final is technically Thursday of next week. I'll give people the option of taking it early on Tuesday, but I'll be here Thursday from 3:15 till 8 o'clock, 7:45. It won't take you that long. Okay. Yes?
What about reviewing the final exam?
Okay, that's why I'm going to give you all these papers back. That's the best review for the final exam. Your earlier test. Okay? And if you have any questions anytime, I asked that several times. I've already asked it several times today. If you have any questions anytime, ask them. And I'll go over any questions you may have. Yes?
The makeup test, you haven't graded it yet, but you will be Tuesday next week.
Okay. I got the stack down, believe it or not, down to that much. Okay?
But it'll be done by Tuesday.
Okay. Actually, all the makeup work has been graded. I don't have it all on Blackboard yet, but it's been graded. It's the stuff from Test 4 and the labs for Chapter 6. I'm still working on those. Okay?
This was test 2.
Okay. It's graded. If you want to see the score, see me after class is over or during the break. There will be a break. Yes?
Tuesday, you'll be in your office.
Tuesday, I'll be in the office. Okay. Let me go over Tuesday again. Tuesday, I'll be in the office from around 8 o'clock, usually a little before 8, until 8:30. Well, close to 8:30. Before 8:30, I'm going to be in 205. That's where I'll be administering a test from 8:30 until 10:20. Then after that test is through, and some of them may take a little longer, so I don't know. But then I'll be back in the office or some room in between 265 and 255, this room, until 3:15. Okay? So that's where I'll be on Tuesday, and you can catch me there. Okay? All right. And if you can't find me anywhere, slide it under my door if you're returning work. Okay? If you come to make up a test, then you need to actually see me. Okay. Any questions then? Yes?
Have you marked me off from the research paper?
What's that?
Have you marked me off from research paper? I already emailed you.
Have I marked you off?
Have you seen his research paper?
Yeah.
If it's not graded yet, that means I haven't printed it yet. Okay? When I print it, I'll grade it, and then I'll put the grade in the book. Okay? Okay. All right. Any more questions? Okay. Oh, one more thing before y'all leave. Whoops. Have you done the student course evaluations?
I already did.
Okay, great. Please do those, folks. Please do those. We've got a SACS visit coming up within the next couple of years, and they will be looking to see what percentage of students do student course evaluations. So please do those.
Most of my classes, the instructor wouldn't give you the time one too.
Yeah. Well, I consider that sort of a form of blackmail. I don't like to do that. But I ask you to please do your student course evaluations. Melanie's here.
Yeah, the thing is, though, there's nothing to it.
Yeah, it's an easy thing to do. It doesn't take long. Do it. Please do them. Okay. Now, any other questions before we get started? As if we aren't started. Okay. Now, Melanie and anyone else who came in a little late, you'll have to listen to YouTube to pick up what we've been talking about. Okay.
Because you don't understand.
All right. As soon as this comes up, we'll get started on Chapter 8. The last chapter we're going to do, hopefully we'll get most, if not all of it, done today. Still waiting for the projector to wake up. Okay, here it comes. All right. Chapter 8 is the only chapter that's mostly dedicated to chemistry. This physical science is supposed to be physics and chemistry. However, the two are intertwined like crazy. So we've already been talking about some chemical type aspects, like thermodynamics is part of chemistry, energy is part of chemistry, temperature is part of chemistry. All this is part of chemistry. But now we're talking about atoms and their periodic properties. So that's what we're doing in Chapter 8. Okay? It begins on page 205 in your big book, and that's probably a number in your little book as well. Okay? And here is the core concept, which is on that page. Different fields of study have contributed to the development of the model of an atom. That doesn't sound very chemical, but it is. Okay? And physics is certainly part of that, and this is part of physics too. So again, they're intertwined like crazy. Okay? Now, beginning in the atomic structure discovered. Okay? Way back, and I think I've mentioned his name before, 460 to 362, somewhere in that time frame. I don't think he lived that long, but that's 98 years. But somewhere in that time frame, Democritus came up with a theory. Now, he was a natural philosopher in ancient Greece. Okay? Now, he came along actually before Aristotle, certainly before Plato, because he followed Aristotle, I think, and before Socrates even. Okay? One of the early natural philosophers. And he came up with this concept, I think I've mentioned it before, that if you had, say, a piece of iron, and you broke the iron into two pieces, it's still iron. And you broke the smaller piece into two pieces, it's still iron. And you keep breaking it down and breaking it down and breaking it down until finally at some point you can't break it down any further and still have iron. That was Democritus' thought experiment, you might say. And he called this indivisible particle, that smallest unit of iron that is still iron, an atom. In the Greek, that means indivisible. Okay? The word atom, or where we get the word atom. Okay? Now, he said it sort of almost has to be that way. Of course, they didn't have the tools to do that. They couldn't break things down to the atomic level, but theoretically, in a thought process, he said there has to be some smallest particle that could be called iron, that you cannot divide it any further. Okay? Now, later came Plato and Aristotle. And they said, oh, no. All matter is continuous. It's just a continuous process. You can't break it to the smallest piece. No matter how small you could go smaller, and it's still iron. Okay? So, he says they said matter is continuously and infinitely divisible, which really doesn't make a lot of sense. Okay? Now, that was all BC. Okay? Way back BC. Okay, and basically after Plato and Aristotle, people sort of forgot about Democritus, so his writings were still there. Because everybody believed Plato and Aristotle especially. Well, then much later, much later, and actually because of Aristotle, okay, when Europe was finally waking up from the Dark and Middle Ages, and they were discovering some of this early thought process, Aristotle has said there's only 4 elements in nature. That's all. Earth, wind, fire, and water. Okay? 3 of those made a singing group. Okay? Y'all don't remember that. You probably do. Okay. All right. Yes. Now, if you think about that, if those are the only 4 elements there are, earth, which is plentiful, free, wind, air, that's plentiful, free, water, that's plentiful and free, and fire. Well, that may cost a little bit, but anyone can make heat or fire. Okay? Well, number 1, we know earth materials are compounds and mixtures. Fire is not even an element. It's a form of energy. Wind is a mixture of compounds and elements. And water is a compound. Okay? H2O. So none of those were elements. But at the time, people believed Aristotle. Everybody believed Aristotle. So the Europeans, clever that they were, started saying, hey, if these are the only 4 elements, and they're absolutely close to being free, then we can mix them together in certain ways and heat them and mix them and combine them and do whatever, and we can make gold and platinum and silver. If these are the 4 elements, we should be able to make anything we want to from those 4 elements. That's the definition of it. So here these European scientists started going crazy trying to find ways to mix and combine and change and stuff, grind it down to the smallest possible thing. These elements, they thought, trying to strike it rich. Okay? Well, after a very short time, they found out we'd better keep some pretty careful records because we're going to wind up reinventing the wheel, going over the same stuff over and over again. So they started documenting what they did, what the results, what they added, what they did, how they did it. And so they were called the alchemists. The alchemists came up with all this stuff, and they started discovering all sorts of things. But they didn't figure out how to make from those 4 elements gold or silver or platinum or those really expensive metals. But they did find out a lot about how things are put together. And after a while, a Frenchman named Lavoisier, with the help of many others, had developed a list of what they considered the real elements. There were something around 37 or so of those, and some of them were elements, and they still counted caloric, which was heat, fire, as one of them, though they couldn't isolate it. But they did narrow it down to many more elements than those. So when they started all that process, John Dalton came along in the early 1800s, and he said, look, folks, it looks like the atomic theory that Democritus did 2,000 years earlier okay, more than 2,000 years earlier, that looks like the way things were. Forget Aristotle, he was wrong. He was wrong about the elements. He's wrong about matter being continuously and infinitely divisible. There had to be some smallest unit here called an atom for every one of these elements, pretty much, that Lavoisier had identified, and others. Okay? Now, John Dalton had an interesting take on it. As these alchemists and later chemists were studying these things, they found out that certain materials went together in certain ratios. Okay? And they called this the law of definite proportions. If you had 2 grams of hydrogen and 16 grams of oxygen, you came up with 18 grams of water. If you had 10 grams of hydrogen and 18 grams of oxygen, you still came up with, 16 grams of oxygen, you still came up with 18 grams of water, and you had 8 grams of hydrogen left over. Okay? It only would combine in certain proportions. Okay? Not just water, but lots of other things as well. Everything, he thought. So he came up with this idea, and it was just an idea. I don't think he really thought it was what the case was, but he said it looks like certain atoms have a certain number of hooks on them. Okay? Carbon had 4 hooks, oxygen had 2 hooks, hydrogen had 1 hook, and he said they always combine by these proportions in some sort of way to take care of all those hooks. Okay? Now we know today that's not the case, but actually he was really onto something. Those are what he was calling hooks, or basically. Huh?
He was just guessing.
Yeah, he was guessing because things went together with these certain proportions. Always, okay? And what it turned out to be, rather than hooks, was unpaired electrons. Now, he didn't even know what an electron was, so he couldn't have named it that, but that's what his hook turned out to be. We'll get to that a little bit later, okay? So here's Dalton's atomic theory. All matter is made up of indivisible atoms. Now, they may be incredibly small, and they are, and he still didn't have the technology to see them or isolate them, but that was his theory. All matter made up of these indivisible atoms. Excuse me. Okay. An element is made up of identical atoms. Excuse me. Okay? Say iron. That is an element. All the atoms in iron are iron atoms. Water, however, is not an element. It's a compound. Okay? We'll get to that later. So different elements have atoms with different masses. There's another difference of his. Okay? Different elements have atoms with different masses. Now we get to the compounds. Chemical compounds, such as water, are made up of atoms with specific integer ratios. There that ratio is again. Law of definite proportions. Okay? And the 5th point, atoms are neither created nor destroyed in chemical reactions. They're all still there. They will take on different forms. You may not be able to recognize them once a chemical reaction has occurred, but they're still there. Generally, most of these reactions can be reversed, and you get back exactly what you put into it. Okay? Those are the 5 specific points of Dalton's atomic theory. Okay? Yeah, I'll leave it there for a little bit. All right. Let me give you some examples. I think we've said this before. Okay? I think we went over this. What is sodium? Did we talk about what sodium was? Sodium is a very soft, technically a metal, but soft, not something you want to build a building with or anything. In fact, you can't. Okay? And sodium is incredibly highly reactive. Okay? And what we mean by that, sodium is going to combine with something no matter what. Okay? if you go to a chemistry lab and you see some elemental sodium there, it's always going to be underneath a layer of oil. It doesn't react with oil. But the reason it's under a layer of oil, if it were to even touch a water molecule, at least one sodium atom is going to basically have such a violent reaction and give off so much heat. You know, it's
what kind of sodium is this?
this is just sodium. Not okay. So sodium is sort of a yellowish metal, soft yellowish metal that is incredibly reactive. It's explosive when it is in contact with water. Literally. Giving off incredible amounts of
They
heat.
use it in paper mills.
Is what?
I think they use it in paper mills and break down paper.
Pure sodium? I think maybe you think it's sulfuric acid they use to break down that, and other things as well. Okay, so that's what sodium is. Now chlorine, on the other hand, so sodium is an explosive metal when it's in touch with water. Okay? And chlorine, anyone know what chlorine is? It's what?
Clorox.
No, it's in Clorox, but it's a green, poisonous gas. You would never want to breathe in any chlorine gas.
They use that in paper mills, I know.
They may, okay?
Well, I know because they have safety issues on chlorine gas, where it goes.
Oh, absolutely, yeah. Okay. So here we have an explosive metal when in touch with water, soft yellowish metal with a green poisonous gas. If you combine them chemically, what do you have?
Salt.
Yeah, you have salt that you
NaCl.
eat on your food. Okay?
NaCl.
NaCl, exactly. And it has none of the characteristics of sodium, none of the characteristics of chlorine. It's a completely new material. It's a white crystalline structure, crystalline compound that we eat, we consume. Okay? Because it's incredible. And it's not that chlorine you lose any chlorine or you lose any sodium. You have them all there, but now they combine chemically to become brand new, totally different materials. These compounds.
They have the salt mines down in Louisiana.
Second?
They have the salt mines down in Louisiana.
Uh-huh.
How did that happen?
Okay. What probably, and this is a guess, there was probably
Your theory.
yeah, there probably was an old seabed there that was underwater.
That's all.
Salt water, had salt in it, and then when the sea receded, the salt was left over. Because, frankly, I know this in Georgia, and I can approximate it in Alabama. They have what they call the fall line. It goes from Augusta, Georgia, curves around to Macon, Georgia, to Columbus, Georgia, which, of course, would then hit around Auburn, Alabama, maybe a little north of there, Montgomery, Alabama, probably Selma, some region there. That's called the fall line because at one time that was below sea level. When the seas were up,
Oh, yeah.
that was the
Alabama
beach.
underwater. I can remember following my grandpa with a view cloud and it shelled.
Yes, exactly. Exactly. That was beneath water. Okay? So it's not at all surprising that probably all of Louisiana, or most of it, was probably below the fall line. And so more than likely there were salt beds there from when it was underwater, and when the water receded, the salt beds stayed. So yeah, not at all surprising. They didn't combine sodium and chlorine. Sodium and chlorine seldom exist as elements. They're too highly reactive to do that. So they always form these other chemical compounds mostly. Okay. Now let's go to that thing of the electron. Okay. J.J. Thomson in the late 1800s. Now remember, John Dalton was early 1800s. So almost a century later, here came J.J. Thomson. Okay, Thomson, not with a P, just Thomson. Late 1800s, performed an experiment, and by this time they had much better equipment. And this one was called a cathode ray tube. Okay, what it did was fire particles, okay, across a vacuum, okay? And these particles knocked off other things, and he discovered one of these things being knocked off was a negatively charged particle. Incredibly small, okay? Almost massless, but it had some mass, but it was very, very small. And but it had a full negative charge, okay? How could something that small have a full negative charge, okay? And all he could do was measure the electron's charge to mass ratio. He couldn't measure its mass, he couldn't measure exactly its charge, but he could determine its charge to mass ratio because he could see how it was deflected in the magnetic field. In fact, cathode ray tube used the magnetic field to send the ray out there. Okay, so he identified the electron as this fundamental particle of matter. Okay, and it is one of the smallest particles in matter. It's a fundamental particle. Okay, now here's what a cathode ray tube looked like. It had to be close to a vacuum. If there were any air molecules in there, things go haywire. Okay. What he did is set up a very high voltage, a negative across one plate, positive across another plate, incredibly high vacuum in a vacuum, and then the anode was a positive plate, the cathode was a negative plate, and what happened, the cathode rays, which went from the cathode to the anode because of the very high voltage across it, those turned out being electrons. Okay. They call them cathode rays, but they turned out being electrons. They could have been some other negative ions, but by and large, they turned out being electrons.
How could he see that?
Huh?
How could he see that?
He could not see it, but he could measure it. That's the key. And he could measure that there was a charge going down there from one to another. It had a certain mass. And what he did was those cathode rays he put between a magnetic field, strong magnet there, and he could see them bend. And that's how he knew he was able to determine the charge to mass ratio. Couldn't determine the charge or couldn't determine the mass, but he could determine the charge to mass ratio. Okay? So that was his discovery, was an electron. All right.
Pretty smart fellow.
He certainly was. Here's what we're talking about here. I'm sorry, I said, well, it's two things. Between two charge plates, okay, here's the anode, the cathode, the anode, which was the negative, the cathode, which is a negative plate, and I guess this is the anode. The picture is not very clear here, but anyway, the rays that come through there, that get sent through there, he has charged plates here, put it in a magnetic field, and now would he have known this at that time? Possibly. Yeah, he would have, for sure. That a moving charge induces a magnetic field. Remember we studied that last chapter. A moving charge induces a magnetic field. We saw that in the lab. Moving charges induce a magnetic, a moving charge induces a magnetic field. Okay, a changing magnetic field induces current, but that's not what he's dealing with here. So he has the charged plates inside a strong magnetic field here. Okay, and as these charges move along here, they are bent toward these charged plates. Okay, and the amount of the bending at the speed they're going, that enabled him, and he had a detecting screen here, and he was able to figure out on average what their charge to mass ratio is. And that's all he could do, okay? The positive and negative charges are deflected in opposite directions by the plates and by the magnet here. And the deflection depended on the charge to mass ratio of those objects. And the electrons he identified by their charge to mass ratio. Okay? Now, later, now that was late 1800s, Within a decade or so, here came another guy named Robert Millikan, around 1906. And I've actually done this experiment as part of a graduate lab I took in physics at Georgia Tech when I first got out of the Navy and went back to grad school. And what they did was have some oil droplets. And basically what I'm talking about, just picture, this is a gross picture perhaps, but an atomizer. The bulb, say that your wife or mom or someone would spray on perfume, little bitty tiny droplets, but this time it was just oil, okay? Tiny little droplets of oil, okay? That you did it with what they call an atomizer, squeezing and sending these out there, okay? So these charged oil droplets, okay, they're oil droplets, and they put in a strong electric field so they pick up charges, okay? The charge on the droplets are multiples of these electron charges because these electrons are individual particles that have a fixed charge. So all the charge that would be on a droplet, it could have 1 electron, 2 electrons, 7 electrons, 15 electrons, whatever, but they all were multiples of a single electron charge, okay? And then he put it in a strong electric field, and as they picked up these charges, then the droplets, which were falling due to gravity, and you could see it, and I'll show you the setup here. Here was the oil sprayer up here, and there was just one little hole at the top that these droplets could fall through. And if there was no field there, the droplets all fell at a fixed rate. Acceleration due to gravity. That was fixed. Gravity was pulling it down. But because you have these strong fields here, negative charge here, positive here, electrons were moving up this way. Same electrons that J.J. Thomson had discovered. And as these droplets picked up electrons, okay, they were repelled by the negative plate, attracted to the positive plate. So now he could figure out what that least common multiple was. That was the charge of a single electron. Because he knew that all those charges, some of those droplets would slow down, some of them would actually stop, some of them would move back up, all defying gravity. I'm not going to sing from Wicked, but whatever. Okay. But defying gravity, as they picked up these charges, they would slow down and then ultimately start moving up. So he calculated how much charge that could be, and from that he came up with an actual figure for the charge. Then he combined with Thomson's charge to mass ratio, and he could come up with electron mass, which turned out to be, like I said, incredibly tiny. Okay? So that's how, with first J.J. Thomson, then Millikan's oil drop experiment, they were able to come up with the charge, the mass of an electron from this. Thomson's result was the charge to mass ratio was an incredibly, actually a large number, 1.7584, that's a lot of precision there, times 10 to the 11th. That would be 175,840,000,000. That's 175, what would that be, billion coulombs per kilogram. But a kilogram is a pretty big mass. That was the charge to mass ratio. Millikan's result was that the charge was 1.60 times 10 to the minus 19 coulombs. If you remember, coulombs measure charge. And then when you combine those together, the discharge divided by that charge to mass ratio, that gave you a mass for an electron of 9.11 times 10 to the negative 31 kilograms. So that's 0.91100000000. You had 9 sets of 3 zeros there for another 27 things. And that was the mass of an electron. Incredibly, incredibly small. Okay? So that's how we came up with knowing both the charge from Millikan's result and the mass from using Thompson's result from charge to mass ratio with Millikan's result to get the mass of an electron. Incredibly tiny. Okay? Now, let's go back a little bit. So Dalton came up with this concept that atoms are indivisible. Thomson and Millikan's experiment, more than 100 years later, gave you a concept that the electron mass are incredibly small and no measurable volume. You knew they were there just by the charge, but you couldn't measure the volume by any means whatsoever, but you could measure the mass. What was the nature of the atom's positive charges? Well, J.J. Thomson came up with a model, and it was that there's some mass out there, a positive mass, and these electrons are embedded in that positive mass, and he called it the plum pudding model, that the electrons are embedded in that blob of positively charged matter like raisins in a plum pudding. Now, I'm not English, so I don't know what plum puddings are. Why wouldn't they be plums in a plum pudding? But no, he said raisins in a plum pudding. I don't know enough to get into the dietary part of it. But anyway, that was his model. Okay? And people say, hey, sounds good to me. Let's assume that that's what's working here. That's the way you can balance the positive and negative charges and you have neutral atoms.
Still writing.
What's that? Oh, yeah, okay, still right. Sorry. So, and this is how science evolves. I mean, you observe nature, you see what's there, you come up with a model, like Dalton's hooks, okay? Yeah, you probably doesn't really think there are hooks, but they act like hooks. Later we found out, well after his death, that those are probably unpaired electrons, okay? Well, Thompson said, well, maybe there's this blob of positively charged mass, much more massive than the electrons, and the electrons are just scattered around in there like raisins in a plum pudding, okay? He must have liked to eat, I do, but anyway, that's what his model was. So what do we do when someone comes up with a model? We test the model. We see, well, let's figure out what's that blob of positively charged matter is like, okay? So here came the next dude, and I'll wait till you finish writing, and his name was Rutherford. I'm trying to think of his first name, but I don't see it here. Ernest, I believe it's Ernest Rutherford. Okay, I don't see it here, but I believe that's right. Now, I forgot there was a thing up there, and I'm going to go back to it now. Okay, after you finish writing. Not quite going to get to Rutherford yet, but when I just turned in the page, I realized I'd left off something I probably should have mentioned. Okay, what Rutherford did, he took, and y'all know what aluminum foil is, right? You can roll aluminum, the metal aluminum, heat it up and roll it into incredibly thin material. Now, you have heavy-duty aluminum that you might drill with, or much lighter aluminum, and you can even roll it much thinner than aluminum foil. Okay? Guess what? Gold rolls even thinner. Have you ever heard of gold leaf? It's a very, very thin sheet of gold, so thin, and you can take, say, a pencil or your finger actually, and rub it on something, and it makes it look like gold, but that's really wood or plaster or anything underneath, but you make it look just like gold because the gold coats the surface of it. And gold is very malleable, so you can do that. Well, we'll get to Rutherford's gold in just a minute. Everybody got this down, this slide? Let me go back a couple slides. It was on here and I forgot to mention it. Here, when we're talking about the atom. This is an artist's rendition of an atom. Okay? Now, the one reason I sort of skipped it, we haven't identified what these things are. Well, let me go on and mention them now. The purples, and I don't know which are which, and the blues, I'm going to say the blues are, let's call them neutrons, and the purples we're going to call protons. Okay? Look how big they are. Okay? Pretty massive. The protons have one charge, a positive charge. Now, these little bitty specks you see here are locations for electrons. You can hardly see them from where you're sitting, probably, and they probably are too big to be actually represent electrons compared to what the protons and neutrons are. So protons and neutrons have a definite volume and a definite mass, and they're really massive compared to these electrons. About 10,000 times as massive as the electrons are. And yet the electrons have one negative charge, that big old proton, only one positive charge. Neutrons, absolutely no charge whatsoever.
Since the word neutral.
Neutral, exactly. Okay. So, proton positive, neutron neutral, not negative, neutral. And then electrons are negative. Now, the electrons, they don't know really where they are at any time. They're somewhere. Some of them may be in an inner shell, some of them in an outer shell. But this is way before any of this. This is now what we think they kind of look like a little bit. Okay? I just happened to see that in the book and I thought I should have mentioned it. But we are building up to that. We haven't gotten there yet. Okay. By the way, there is a case study on the top of page 208 on the discovery of an electron, and then the one on 209 looks like it's part of the same one, not quite, but this is the oil drop experiment that Millikan did, that when put together they came up. So you can read that a little more detailed than probably what I gave you. All right. There's the oil drop experiment. There's the calculations. And there was our model. So here came Ernest Rutherford. Okay, I knew his name was there somewhere. 1907, which is just a year after Millikan's oil drop experiment. So things were happening a little bit faster now. But J.J. Thomson had come up with his plum pudding model. So Rutherford said, let's test this and see what this plum pudding is like. You know, what this positive blob of stuff is like. So what he did, he took, and they knew about these by now, alpha particles. Does anyone know what an alpha particle is? It's a type of radiation, but it's a type of radiation that's really not super bad, because if you have a piece of paper, it'll block alpha particles from touching you. They don't go through things very fast or well. Okay? They're the nucleus of a helium atom, is what they really are. 2 protons and 2 neutrons, no electrons. So they're plus 2 charge. Now, you don't want them getting on you, and you certainly don't want to ingest them or eat them or get them inside your body, breathe them in or anything else, because they can cause damage. They're radioactive materials, okay? So you do want to stay away from them. But in a very carefully planned and well-protected experiment, what he did, he scattered some alpha particles. He produced them. How he did this, I'm not absolutely certain. But he fired them into this gold foil. Very, very, very thin sheet of gold. Okay? Now, this is a picture of this experiment. Okay? Scattering these alpha particles off a gold foil. Now, what he was expecting, because of the plum pudding model, was that the electrons would be scattered all over the place. So he has this detection shield that goes all the way around this, and he figured they were just going to be bouncing off that gold in all directions and going through just sort of scattered at random. But he hoped to be able to tell something about what that positive plum pudding was like. Okay? Because remember, the alpha particles are plus 2 charges. They are going to be scattered by that positive blob, okay, and sent backward a lot, whereas the electrons are a negative charge, but they're so tiny, so incredibly tiny, probably not going to be, attracted much to them. So he hoped to get an idea of what the plum pudding, how the raisins were distributed in the plum pudding, basically. Here was his surprise. Most of those alpha particles went straight through the foil. They weren't deflected back by that positive blob. They went straight through with no deflection, significant deflection at all. Went right through, as if that, in fact, the plum pudding wasn't even there. Okay? And he found out, no, there is no mass of positively charged substance that held the electrons in place. It was something very different. Now, a few were scattered big time in the opposite direction. Okay? And then there were some that went in various things. His conclusion, the atom's positive charge doesn't reside in some generic mass that contains the electrons. The positive charges reside in an incredibly small, incredibly small, but incredibly massive nucleus. That basically all the mass of that atom is, now this is probably not a good example, but I'm going to make it up, and it's probably fairly close to reality. If you had let's imagine this room was filled with water. Imagine it was filled with water. It has a pretty big mass, right? If this was an atom, it wouldn't be rectangular shaped like this, it would be spherical. But all that mass would be concentrated in one little drop right here. The entire mass in that little bitty drop. And then the electrons, that's your nucleus of the atom. And the electrons are flying around. They have almost no mass at all. They have a little bit, but very, very little. And they're flying around all the rest of the volume of that atom. So, your mass is concentrated on an incredibly small, but incredibly massive nucleus where those protons and neutrons live. That's what we saw in that earlier picture. But the electrons, almost no mass, are flying around just like the air molecules in this room, flying around wherever they want to in the thing. Now, my older brother, when he came home from college, sophomore year I think it was, he had just taken his physics course, and he really liked that physics professor. And evidently this guy had explained this phenomenon that almost all the mass is located in an incredibly small nucleus, and then the electrons take up most of the volume. They have almost no mass at all. So what's in between them? Nothing but empty space. And so his statement was, most of everything is nothing. Meaning most of the volume of everything, lead, gold, whatever, is absolutely nothing there. It's empty space. Electrons flying in empty space, but the whole mass is concentrated in a very tiny little nucleus. Now that picture we saw earlier was probably way too big of a nucleus and way too, not nearly the right range for the electrons, but it was something more like that. So later they discovered the positive charges were protons. Now they don't tell us who discovered that. It probably was a team of people, and they never identified just one. But finally, later, this is 25 years later, they found out the rest of the mass of that nucleus wasn't all protons, but most of it was in neutral particles, almost the same size and mass of protons, but called neutrons. Now the funny thing is, even though the protons have a small positive charge, and the neutrons don't, the neutrons are slightly more massive than the protons are. Not much, but just a little bit more massive. About the same size, but just a little more mass. And James Chadwick I think another British physicist discovered that. So if you haven't been following it, back with electricity and magnetism, a lot of that was more Southern Europe, Volta in Italy, Galvani I think was Italy, but then Coulomb and Ampere and stuff were from France. They were the honchos at the time. They were the most advanced societies. They had more time and money to spend on research. By this time, Britain has now taken over and is sort of running the show, because a lot of these names, you'll see John Dalton, Rutherford, Chadwick, those are all very British sounding names. I think most of them were. J.J. Thomson, I think, was British also. Okay. Now, so here's what was happening. The alpha particles being shot in pretty much a straight line, okay? And they're just representing this gold foil. And you think of gold as pretty dense, and it is, but you can roll it out really thin. And they thought it was so thin that they had maybe no more than 3 or 4 molecular layers thick, okay? Surely there's enough plum pudding there to bounce back most of those alpha particles. No. Most of the alpha particles went right through. And why is that? Because all that mass was concentrating in a tiny little nucleus, and most of the volume was that electron cloud that didn't really affect it at all. So most of these rays could go through without being influenced by a positive nucleus at all. And here's Trent. Okay. Does anyone else come in? I didn't catch you to call your, identify your role. And only when they hit close to a nucleus, then they were bounced back. And they were really deflected big time. But most of them went straight through, not being, because most of everything is nothing. It was just that electron cloud that had nothing, no influence on those alpha particles. Okay? So that was Ernest Rutherford's gold foil experiment that showed, nope, plum pudding is out. Nucleus, tiny little nucleus containing the positive charges, big cloud of electron with almost no mass at all containing the negative charges. So, did everybody have that? Okay. So what is this nuclear atom then? Okay? Remember, all elements are made up of the same types of atoms, okay? And all these atoms, every element is about the same mass. These atoms are about the same mass, but they're all different from all the other elements. All have unique masses. Okay? Well, what makes up a material, an element, is the number of protons. If it has one proton only, that's hydrogen, and can't be anything but hydrogen. If it has 2 protons, that's going to be helium. 3 protons is always going to be lithium. 4 protons, beryllium. 5 protons, boron. 6 protons, carbon. 7 protons, nitrogen. 8 protons, oxygen. 9 protons, fluorine. 10 protons. Oh goodness, what is it? One of those bubble gases. Huh?
You make a song like that, 12 Days of Christmas.
Yes, the 12 protons of the periodic table or something like that. But every one of them makes up a unique element. And the number of protons determines what element that is. Okay. Elements are distinguished by that atomic number. And by the way, that's what we call the atomic number. How many protons are in that atom? That's the atomic number. Okay? And if you know the number of protons in there, you know exactly what element it is. Now, they say here on this slide 113 elements have been identified, unique, different elements. Let's see if the book has something more, because this is an older slide. In our book, a little bit more recent there, 118. So you can change that 13 to an 18 if you want to. It probably is more than that now because, let me make it blue. Let me try dark blue here. The book says 118 elements, okay, have been identified. There may even be one or two new ones since the book was published, okay? Now, the number of protons equals the number of electrons if they're neutral atoms, okay? Otherwise, they're not neutral atoms, okay? Now, I think we've mentioned this before. If the number of electrons is not equal to the number of protons, they're no longer called atoms, they're called ions. Remember, the alpha particle was the nucleus of a helium atom, so it's an helium ion, a +2 charge. 2 protons with no electrons, okay? So if the number of protons equals the number of electrons, you have a neutral atom. If it doesn't, you have an ion. If you have excess electrons, it's a negatively charged ion. Deficit of electrons, it's a positively charged ion. Guess what? You don't gain or lose protons, ever. That would require a nuclear reaction to do that. No, we don't do that. In chemical reactions, the only things that make these ions are changing electrons. It's all the electrons that are gained or lost. Okay? Now, even though every nucleus of every element has the same number of protons, they don't have the same number of neutrons. Okay? And this makes up, when they have different number of neutrons, then you have what they call isotopes, different isotopes of these various elements. And here's Brian. Okay. Watch out. Okay. Goodness gracious. Time is going away with us here. Okay. So let's talk a little bit about that. Now, we're going to show this slide several times, okay? So get used to it, okay? Most hydrogen has a single proton and, of course, then a single electron, if it's a neutral hydrogen atom. That's all there is. A single proton with one electron floating around, randomly moving all around it. You never can tell right where that electron is, because it just is moving all the time. The best they can do is say it's a good probability it's somewhere in there, because they're almost massless. It's hard to determine. So that's your normal hydrogen. Okay, now what are these numbers here? Now I said one proton, no neutrons. What these numbers stand for is the atomic number is always lower left. Hydrogen is always got one proton. If it doesn't have one proton, it's not hydrogen. Okay? But if it has no neutrons and just that one, then its atomic mass, and that's what the mass number is also 1. Because electrons have almost no mass. So the number of protons and neutrons add up to be your mass number. And since it has no neutrons, its mass number is also 1. Most of the hydrogen in this room and anywhere in space is 1 proton alone. I'm guessing something like 97 to 99% of hydrogen is a single proton with 1 electron. However, every now and then you'll find a hydrogen with a neutron. It's still hydrogen because it has 1 proton and only 1 proton. But every now and then you'll find a single neutron combined with that proton in the nucleus. Guess what it's done? Doubled the mass of that hydrogen atom. Doubled it, okay? Because you added another neutron. Actually, the neutron's a little heavier than the proton is. So it basically doubled the mass. So we call that deuterium. 2, because its atomic mass is now 2. It has a proton and an electron. I mean a neutron. Proton and a neutron. The proton is the mass, is the atomic number. The sum of those is the mass number. One time out of maybe a few thousand, maybe close to 1,000,000 times, maybe just a few hundred, tens of 100,000 times, you'll run into a hydrogen atom that has 2 neutrons. Still 1 proton, otherwise it's not hydrogen, okay? So it still has a 1 here, but now with 2 neutrons, that has a mass number of 3. That's called tritium, because it's 3 times as heavy as normal hydrogen. That's a pretty significant change, okay? Now, so what? It doesn't happen that frequently. Why are we even concerned with it? One thing that neutrons do for you, they sort of absorb radiation, okay? So what, and if you hadn't noticed it, every nuclear power plant that you'll ever see is usually located on a river, except for some of those like in Japan that are located near the ocean. Now, 2 reasons they're located near big sources of water. Number 1, the nuclear reaction is heating that to make steam to fire through the steam turbines. So they got to have a good supply of water. But the second reason is, I think at just about every one of those plants, they have centrifuges that are spinning that water around like crazy, trying to find the heavier water. The heavy water has either deuterium or tritium in it. And it's very, very rare, but it's there. And they isolate that heavy water that has deuterium and tritium, and then they use that in the rods that they push into and pull out of the reactors. To pulling them out speeds up the reaction, pushing them in slows down the reaction, because those extra neutrons absorb the energy from that making the chain reactions occur. So that's what's happening. If you ever watch Star Trek, they always fiddled around with the tubes. Remember, push them in. Y'all too young to watch Star Trek.
We listen to that.
Okay, right. Okay. So anyway, that's how we identify the different isotopes. They all have the same atomic number, okay, because they all have the same number of protons, but they may have different number of neutrons, so the mass numbers will change. Always by a single digit, okay? 1 to 2 to 3, something like that. All right. Sort of makes sense? Okay. They have all the same characteristics as hydrogen, deuterium, and tritium, except it's more massive. Okay. So, here's what these atomic symbols stand for. The mass number is the number of protons and neutrons added together. Your lab coming up on Tuesday, you're going to have to remember this. The atomic mass units, and that's called, they used to call them AMUs for atomic mass units, now they just call them U for units, is 1/12 of a carbon-12 isotope mass, which is a rather strange thing to do, but carbon is a fairly common material. It's easy to isolate, so they say 1/12 of that. That is 1 mass unit, okay? Your atomic weight is the atomic mass of an element averaged over the naturally occurring isotopes. So, for instance, hydrogen will be a little bit more than 1, because there's a few deuteriums out there every now and then, and very rarely a tritium out there, so its average will be a little bit more than 1, okay? 1 atomic mass unit, okay? Carbon-12 is going to have exactly 12. That will be its atomic mass, because that's how we identify it. But because there's other carbons out there as well, carbon-14, for instance, that's going to bump it up a little bit. Okay. So, it's just one of the naturally occurring isotopes. Every now and then you'll have too few neutrons. More likely you have too many neutrons. Okay. Or excess neutrons from what's normal. So here's this slide again. They love this slide. This is how we name it. The atomic number is in the lower left. The mass number is in the upper left. Okay. The symbol for the element is there. So pick another element. Name an element. Any element. Fe, iron. Okay. If you go to the periodic table, and hopefully your book has it somewhere near the front or back inside cover, you'll see iron down here. Fe is atomic number 26. That means it has exactly 26 protons. Exactly. Now you look at its mass number, which is underneath here. Now this isn't set up just like this, but similar. It's 55.85. So let's round that to 56. How many protons would it have? 26 is its mass number. 56 is its 26 is its atomic number. 56 is its mass number. How many neutrons would it have? 26 from 56. Or high-level math. 30 neutrons on average. But because it's really 55.85, there are some other isotopes out there that only have 29 neutrons. And maybe a few that have 28 neutrons. There may be one or two out there that have 31. I don't know. I don't know all about iron. But that's why the mass numbers are usually decimal numbers. The atomic numbers are exact, because that's exactly the number of protons you have. Because the neutrons can vary, the mass numbers vary generally. Okay? So, goodness, it's heavy holding that up. Okay. All right. There's a blurb at the top. It's also called a case study. This chapter has lots of case studies right in a row here. Discovery of the nucleus, which you would, I guess that's sort of attributed to Rutherford, because he's the one who did that experiment that found out it wasn't plum pudding, but actually had a nucleus there. All right. Now, what we've been calling the mass number is often, well, the mass number would be, this would identify a particular isotope. Then this number is always going to be an integer. Okay. But the atomic weight, which is in the periodic table, that's going to be the average over many different isotopes. And that's why it's a decimal number. Okay. So that's, you'll find me saying atomic weight. No, that's really the mass number. And then we'll use atomic weight to be the average of all this. Now here, these are chemists here. They're mixing up weights and masses. We know they're different in physics, but they're treating them as if they're the same. Shame on them. Okay. They do show as a table on page 210. I don't think they're going to show it on the slides. They show sort of one outtake from that, okay? Let me make sure they don't know. Okay. This down here at the bottom. The table 8.1 that's on page 210 of your book, okay, it shows stable isotopes. Here's what we call hydrogen. It's 1,1 that we've had several times before. Compared to carbon-12, it's a little bit heavier. Not much, 1.007. That's almost 1. Okay? Its abundance, 99.985% of the time. That means 15 out of 10,000 times. 100,000 times. 15 out of 100,000 times you'll find the deuterium. Okay? Or you'll find something that's not plain hydrogen. Okay? With one proton, one electron. Deuterium, on the other hand, because it's got a proton in there, its mass is 2.14. So it's more than double the mass. Okay? And its abundance is that 0.015. See, the tritium would have to be so many decimal places further out there before you detect tritium. Okay? It's really rare. Okay? So that makes the atomic weight. What you do is multiply this by 99.985%, multiply this by 0.015%, and you add those two together and you get what the atomic mass is, 1.0079. See, hydrogen alone is 1.007. All this other only does a fourth decimal place, almost one more third decimal place, but not quite. So here they've done the one for nitrogen. On your table here, it shows nitrogen 14 and nitrogen 15. Because nitrogen is nitrogen because it has 7 protons. Can't be anything else. And no nitrogen will ever have anything other than 7 protons. However, most nitrogen has 7 neutrons as well. But not all. That's 99.63% of the time. That means 37 out of 100,000? Yeah, 37 out of 100,000 will have an extra, will have something other than 7 neutrons. Okay? And it's 14, nitrogen 14 has a atomic mass of 14.00307, okay, units, AMUs, okay, atomic mass units. However, that one time or 37 times out of every 100,000, you'll get an extra neutron there, making it nitrogen 15. That's 0.37, which would be 0.0037, okay? And then you multiply that by its atomic mass unit, okay, which is 15.0. See, it goes up by 1, approximately, okay? And that then, you multiply this times that. Now, notice they changed the percent to a decimal number, always. So multiply this by that, and this by that, add those two together, that's what your average is, okay? It's not 14.0037, it's 14.006, 0307. It's that, because this bumps it up from what that was. Not much, but just a little bit. Okay. A lot of blah, 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 right? I do want to point out something. Iron that you mentioned was 1. It's pretty far off. It's 55.85. Nothing like this, okay? So there's quite a few iron 29s out there, as well as most of them are iron 30s. Neutrons. 30 neutrons, but quite a few of them have 29. There are a few that are much stranger, like chlorine, 35.45. Almost an equal number of, and chlorine is 17, so the prevailing is 18 neutrons, but quite a few of them, almost as many, have 19 neutrons. So you see, it's not always that one dominates like this, 99% to 0.37%. A lot of them are like that, but some, like chlorine, are 45, 55%, really close to each other, 10%. So you can have some naturally occurring isotopes that have more than just a very rare situation. Okay. Now, concepts applied, they have this thing called atomic parts. You can look at that, read through it. I don't recall really finding it all that useful, but yeah, it really is. If you do the math, it really can show you a lot. Now, the slide set kind of deviates from what the book does right now. The book has changed since they did this slide set. And they threw in something here that really isn't talked about much in the book. Well, it is kind of. The last paragraph on page 210, how are the electrons moving around the nucleus? Okay? That paragraph there shows a dilemma that we have. Okay? The classical atom, okay, if you go by atomic theory and do everything that we've done so far, electrons orbit the nucleus. They go around there, they're scattered, they're somewhere around there. Because they have a curved path, they have to be accelerated. Remember, we talked about that, the planets going around the sun is pulling them in, so therefore they're giving them an acceleration, changing its velocity because it's a curved path. Well, any accelerated charges typically would radiate. If they radiate, they'd be losing energy. If they're losing energy, then they can't go as fast. If they don't go as fast, then they start spiraling into the nucleus, and that would tell you atoms can't exist. But we know they got to exist. We're here, right? So there's a problem here, Houston. And this was that last lingering little problem that physics had at around the turn of the century, beginning of the 20th century. They just couldn't figure out this little problem. But if they get this figured out, boy, we got it knocked. We've got physics tied up in a bow. You can send it for Christmas because we got it done. We don't need much else. But we know atoms do exist. This can't be true, so there has to be something else going on. And that's where quantum mechanics was born. We have auto mechanics and we have quantum mechanics, okay? The quantum mechanics don't make nearly the sense that auto mechanics do, okay? So this leads to the quantum concept, okay? Now they skipped the first name here, but they're going to bring them back later. But actually they didn't. They jumped over them. Let's start where it is. Right around 1900, about the same time all this other stuff was being discovered, a German, and here the Germans come into play. The Brits were rolling the show for a while. Now the Germans are coming in. Max Planck. It looks like Planck, but it's pronounced Planck. Around 1900, came up with a theory, a model that said maybe this is how it works, that it doesn't destroy the atom, okay? That you have little quantums of energy, little packets of energy. They're not quite material, but they're not just a wave. There's little packets of energy. Max Planck came up with that, and he's sometimes considered to be the father of quantum mechanics, okay? Now, just to give you an idea of how kind of revered he is, there are a number of universities that are all kind of linked together in Germany called Max Planck Institutes. Now, their system is very different from ours. We have, say, I'm going to pick on the technical institutes, MIT, Caltech, Georgia Tech, Rensselaer, all these different technical schools. They're all completely independent of each other, scattered across the country, and they compete against each other. Well, in Germany, these universities that do kind of the same things are sort of, not all of them, but a lot of them are under Max Planck Institute. They named it after him, and they have different campuses in different locations. And this is totally beside the point. But we have some really good German friends living in Birmingham. We actually are the godparents for their son. We knew Miriam before she knew her husband Olaf. She came over here on a Fulbright scholarship, very, very bright woman. Came over on Fulbright scholarship, and friends of ours from our church sponsored her as an international student, and got to know her. And they found her so interesting, they invited us to get to know her too. So we knew Miriam for quite a while. She went back to finish her PhD in Germany, then met Olaf. They got married, and then she came back to work at UAB. Yes, sir.
I got an email from you.
Okay. You want me to come down? How late will you be here?
7.
7? Okay, at my break, I'll come down and try to touch base with you.
Sorry.
Okay. Okay. He's one of my math instructors. Okay. Now, so anyway, we got to know Olaf as well. Well, Olaf is from Munich, Germany. And so one time when we were in Germany, we went, and by the way, Olaf's parents had come over, stayed at our house when Olaf and Miriam lived at a fairly small apartment, and they had the first child And so his parents stayed with us, and so we got to know them really well. They were begging us to come to Munich so we could stay with them. Well, when we did get a chance to go to Munich, we stayed with them. So we got to be fairly close with them. We found out that Mr. Cooch had retired from Max Planck Institute, which was just the next train stop up the mass transit line from where he lived. So he took us up there, and we showed us part of the institute. He could show us all of it, the parts of it. Really, really high-tech, really impressive place. And he worked for him for most of his career. Well, around the same time, and mixed in with this, my wife was working on her doctorate at UAB. This was probably before Miriam came over, and one of her classmates was from Italy. And my wife and Fabio just got along really great, and they really enjoyed each other, and they were recently married, we were recently married, so we got to know Rita and the two couples didn't do a lot together, but we exchanged meals every now and then. We were grad students, they were grad students, didn't have a lot of money, and we didn't either, so we just did little simple things together and had a lot of fun with it. Well, once Fabio graduated, he got a job with a pharmaceutical company up in Boston. His wife loved Boston. Okay, she had gone up there to study English, so she could have studied down there. But she loved Boston, so they moved up there. She got pregnant and had their first child, their son, Giacomo, up there. So he was born in the U.S., made him a U.S. citizen. Okay, so later when we got to visit them in Italy, the family came back. They went back to Italy after a year, and 2 daughters were born. And then they came back when they were in elementary and junior high school, and we got to know the kids then, and they were a lot of fun. Then they moved back after a year, back to Italy again. And sometime several years later, we visited them in Italy, and by this time, Giacomo was like a first or second year high school student. And we really got to know him well. He entertained us, he taught us card games and stuff like this while his parents were working and stuff like that. So we got to know him, we got along with him really well, and that gave his parents an idea. They wanted him, because he was a really bright kid, to go have the option of going, because he was a U.S. citizen, of going to university here in the U.S. or going to Italy, whichever he chose. So they thought he'd have a better chance of going to a U.S. university if he came and went to high school at U.S. So his fourth year in high school, they arranged for him to come to Birmingham, and he came and lived with us for the year. And we were like his surrogate parents and all that went along with that. But it was a real fun year with him. He was a very bright kid, just like his dad. And we had a good time with him. Then he went back to Italy, and they do 5 years of high school. So he graduated at Altamont High School in Birmingham, and then went back and graduated his regular high school in Germany. And then he got to come visit colleges, and we took him around to see colleges. And he got a full ride at University of North Carolina, everything paid for, until he got accepted at Harvard. Nothing paid for. He had to go to Harvard, because that's where he was born, in Boston, and he had to go there. Ran his family into debt going to Harvard. But anyway, he graduated in physics at Harvard and went back, and guess what? He's doing his doctorate now at Max Planck Institute in Munich. So we've been Max Planck all over the place, and our German friend's father worked at the same place where he is doing his doctorate there. So it's just pretty amazing. Anyway, Max Planck came up with this idea of quantization of energy. Einstein, that you probably heard of him somewhere, haven't you? He came up with the idea that light is made up of these quantized, and he called, I think he was one that gave the term, photons. That light is not just continuum that comes out of a bulb, it's actually little packets of energy called photons. And these are the same quantized things that Max Planck talked about. Here is Planck's equation E, the energy of a photon, is Planck's constant, which is 6.63 times 10 to the minus 34 joule seconds. Now, if you remember, a joule is a unit of energy, and it's already a small unit. Now it's 10 to the minus 34 joules, so this is incredibly small, times second. So that made the frequency, that's what you put next, and that's a per second, so this gives you the unit of joule. And this is the Planck's constant. And everything that's been discovered says this seems to be exactly the case. No matter what element or anything you're talking about, that constant is true for all of them. Okay? Now, so light's made up of quantized photons. Higher energy photons, the more energetic, or equals more energetic photons. You have more higher frequency, you have more energy. And that fits Planck's law here. So, that's about where example 8.1 comes into play. And let's see if we can do 8.1. Ooh, we can't do 8.1. Let's do it here. What is the energy of a photon of red light with a frequency of 4.6 times 10 to the 14th hertz? This is red light, by the way. Well, we have, let me get back to black here. If I can get the thing to come up. There we go. All right. E is equal to HF. Okay? We're looking for the energy here. What is the energy? That's the unknown here. Red light has a frequency of, F for red light, is 4.60 times 10 to the 14th. And what is a hertz?
Excuse me, is that supposed to be a B?
Yeah, that's an E.
A B?
E.
Oh.
Energy. Okay. E, this E, that E, they're the same. Okay? My pen's sometimes drag. What's that?
What did you ask what a hertz was?
Yeah, what's a hertz?
It's a frequency.
A frequency. What are the actual units of it?
Hertz.
Okay, it's a hertz, but what is that in fundamental units? It's a per second. That's what a hertz is, a per second. It's how many cycles per second. What do you mean by that? Huh? The frequency is how many cycles in a second.
We're going from trying to remember it from way long time ago.
Yeah, okay. And this is let's see if I can get it right now. 4, 6, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. 4 sets of zeros there, 3 zeros there. And that would be how many cycles it does in a single second. So I mean, that's really high frequency. Not super high frequency, but pretty high frequency. That's cycles per second. And cycle is not really a unit, so it's a per second. Okay? So a hertz is the same as a second to the minus 1 or 1 over second. Any of these can be used to represent a hertz. Okay? So, and H, by the way, is hertz, is Planck's constant, and that is, it was on the previous slide, there it is, 6.63 times 10 to the minus 34 joule seconds. Really small number. So what is this energy? 6.63 times 10 to the minus 34 joule second multiplied by the frequency 4.60 times 10 to the 14th per second. I'll put it 1 over second. Okay, so this second cancels out the per second there, and you wind up with joule. So if you got your calculator, and please know how to use your calculator. 6.63, you look for the key that says EE or EXP. 6.63, EE or EXP, and then you do a negative 34. Now if you're using your telephone, you have to know what its syntax is. Most of the more modern calculators, they have a subtraction key that's with the plus, minus, times, and divided. don't use that key. They have another subtraction key, a minus key, that's in parentheses. That's the one you use here. That's the negation key, as opposed to the subtraction key. So 6.63 EE or EXP, depending on your calculator, then that negation key, 34. Okay, because when you do the E or EXP, you get another little block that you put the negation key 34 in, times 4.6. You don't have to put the 0 if you don't want to. EE or EXP, now you just put 14 for the exponent.
What is that, 4.60?
4.60, and so in the calculator you don't have to enter a 0. Okay, multiply them together and you get as an answer the E equal, what do you get?
Is that times 10 to the minus 14? I can't read it, I'm sorry.
Oh, it's 4.6 times 10 to the positive 14. That thing that looks like a minus sign is the bullet on the thing over there. I ran over. Did you get an answer?
Yes.
What did you get?
3.049.
Okay, we'll make that 3.05.
Yeah. 8.
Say again?
Multiply 10 times minus
Okay.
19.
Times 10 to the negative 19th joules. And remember, a joule's already a small amount of energy. This is really tiny. But you're talking about a single light photon, okay? Those are really small. And that is a fair amount of energy for that, okay? So yeah, that was example 8.1. Okay, 8.2 does it for violet light. In violet light, so the frequency of violet light, that's not violet light, but violet light, purple, is 7.30 times 10 to the 14th hertz, which I will call 1 over seconds. That's what a hertz is. Okay? So all you do is the same thing here, but now you multiply it by 7.30 times 10 to the 14th per second. And again, the seconds cancel out. The 6.63 EE or EXP, negation 34, times 7.3 EE or EXP 14. And what do you get for the energy of violet light? This was the energy of red light. Energy of violet light is, anyone got it? Something around 4.84 times 10 to the minus 34. No, minus 19. I can't read my writing. Joules. Okay? So red light, fairly low energy, I mean not super low. Not a lot of difference, but some difference. Now that bridges the light spectrum that our atmosphere allows to come through from the sun. That's most of what they allow. Higher energy radiation is deflected, lower energy doesn't make it through the atmosphere. Okay? So that's a really narrow band of energy. The red is infrared energy. And below the red is infrared. That's heat. It gets trapped in our atmosphere. That's what global warming is in some senses. Okay? We always had it, whether global warming or not. We trap it because we're far enough from the sun. We wouldn't, if we didn't trap heat from the sun, our atmosphere didn't, we wouldn't be able to live here. Okay? Because we're too far from the sun and we wouldn't be warm enough. Now we're trapping too much heat. That's what global warming is. Okay. Now on the upper end, you have the violet light. What is beyond violet? Ultraviolet. What does ultraviolet do to you? Burns you. Exactly. Causes cataracts. Causes wrinkling. Causes skin cancers. Okay? Okay. You can usually tell the beautiful young bodies that used to be sun worshipers and stayed out on the beach all the time,
Ain't that the truth?
they're now the prunes because their skin is all wrinkled up like crazy. People who try to avoid the sun, they will be much smoother skinned, much longer. I was out in the sun way too much when I was young. I lived on the farm. So, anyway, not quite a prune yet, but getting there. All right. So those are examples 8.1 and 8.2. Okay. Let me clear this off the screen. Okay. And go back. So I think we hit everything here. The higher the energy photons, the more energetic. The higher frequency is more energy. Planck's law. Okay. So now we're looking at atomic spectra. This is the right-hand column on page 211. Sorry about that. Okay, we've been at it now for a little over 2 hours. Do you need a break? I saw somebody get up and do we need a break? Let's try to keep it quick, folks, because we really be a great idea if we could finish the chapter. I don't know that we will. We got a lot to cover. I've been talking too much. But let's give it our best shot. Okay? So come back quickly. YouTube, anyone that this is a little bit of it. So let's look at what they call atomic spectra. Okay? Now what a spectrum is a range. Okay? Now, there's a couple different kinds of spectra, okay, ranges you might say. There's what we call black body radiation, which is continuous radiation distribution. That would be if you were to measure the distribution of infrared radiation coming from our ventilation system, it's going to be a wide range. Pretty much on the high side because there's quite a bit of heat coming out of it. But it's a continuous radiation distribution. Depends on the temperature of the radiating object, okay? And it's characteristic of solids, liquids, and very dense gases, okay? And let's see if they do give an example of that, okay? This is a reasonable facsimile of that. You see light, whether it's sunlight or an incandescent light, fluorescent light, whatever, if you were to narrow that into a very narrow band, send it through a prism that breaks it down by the colors, you see you have basically a continuous spectrum here, from red to violet. Red being the lowest energy, violet being the highest energy. And that spectrum, it goes smoothly through all those, okay? You have a mixture of radiations through all that. You know, it's no specific one thing. Now, on the other hand, we have what we call line spectra. And this is emission at characteristic frequencies, okay? This would be, and the term here, diffuse matter, I can't tell you why they say that. But here's the more important, incandescent gases. In other words, these were very dense gases will produce this. And basically what we're talking about here, you have a filament that's giving off a wide range of energies, and that wide range of energy is going through a gas, probably argon gas, which is interacting with that, and you get a continuous spectrum here. You call that black body radiation, even though this isn't a black body, okay? But if you had a single incandescent gas, and here think lasers, one particular gas there, and it's somehow heated up to glowing, then you will have what they call line spectra. And let's see if they show this. Yeah, this is a little bit. So they showed a tube here. Now that's probably not fluorescent, but it could be. But one tube, probably a tube of a single gas, and then you have lines of color, not a continuous spectrum, but lines of color, an orange, a blue, purple, and then I don't know what that's supposed to be, but some lines of spectrum. Okay, one of the illustrations of that, and we're going to play with this for a while. It's called the Balmer series for hydrogen lines. Okay? If you have pure hydrogen gas, okay, I don't know what was supposed to be here. Let me see if I can find a figure from the book that might show that. I don't think so. I think the one in your book is better than the one they showed here. And that's why I was really disappointed when I saw that. This is what they showed. Here's the continuous one here. They don't even show the lines in between. That's what it looked like. It just smears from one color to another. So you have red and orange tends to yellow, and then yellow tends to green, green tends to blue, blue tends to what they used to call indigo, and then to violet. But if you have a laser or a monogas here, like neon or neon or something like that in a tube, one thing, then you'll have just these very narrow line spectra. That's a far better picture than that. Okay, and you see there's a red at the top, then it skips down to a green, then a blue, a purple, and then another purple. Okay, slightly different kinds of purple. Okay, now what that is leading to is Bohr's theory. Okay, Niels Bohr, and this is where the book deviates a little bit from what the slide set does. Okay, the book started off with the Bohr model back on page 211. Niels Bohr, a young Danish physicist who visited Rutherford's lab over in England or Scotland, wherever that was, became very interested in the questions of the solar system model of the atom, and that's where his model then led to incorporate the quantum concepts of both Planck and Einstein that they came up with earlier. So that's why our book is a little crisscross there. Okay? Here's what Bohr's theory says. 3 rules. Electrons only exist in certain allowed orbits. Okay? Within an orbit, an electron does not radiate. Remember, accelerating charge, which would be by circular orbit, would have to radiate. But Bohr said, no, it doesn't. If it stays within that orbit and doesn't jump in orbit or go down in orbit, it won't radiate. The radiation is emitted or absorbed when you change the orbits. Okay? So that was the concept here. As long as electrons stayed in a single orbit, even though it was in a sense accelerating, it wasn't radiating. Only when it either jumped up a level or more likely fell down a level, that's when it radiated. That's what's happening in these tubes right here. You've got a ionized gas flying up and down the tubes, okay, having energy, and that is usually a mercury vapor ion that's going up and down there. And when it does, it passes the white powdery material that's on the inside of those tubes, and that's a phosphorescent material that when certain energies of ions go past it, it jumps up a level. And this electron will jump up to this level, okay, because it picked up energy, okay? When the ion passed, and nothing to keep it up there, then it's going to fall down that level, okay? And this is a material that level it falls down is just enough to give off 1 photon of light. Now this is fairly bright white light. You can have others of slightly different material, and that would be a soft white, a yellow white, you know, various things like this. I was looking in the store, Home Depot, last weekend. We were getting some additional LED lights. We've been using a lot of our incandescents are blowing out, and a few of our compact fluorescents are ending their life too. And we've actually had an LED or 2 go out on us too. But, so we needed some more, and they had bright white, they had soft white, they had daylight white. I mean, they had a whole series. Yeah.
question is the color of the powder in it sets the,
Is that powder that's on the inside of the
is
tube?
that what makes it, bright light?
Yeah, I think that's it. That's my understanding. It may depend on what
I had a grow light before, you know, growing marijuana.
Oh, really?
I'm
Okay.
just kidding. I got your attention.
Isn't that how everybody wants to come to?
No, I had-
Okay.
No, I had a grow light for
Right.
plants.
Yeah.
And it was, never seen that color before.
Yeah, it's a little more toward the ultraviolet, I think.
But it was good.
Okay, so that's what's
But it's
happening
the
here.
powder anyway.
Yeah, when it falls down a level, that's when the photon, and that photon has a specific frequency depending on the level that it falls down. And that's why the line spectra are certain colors. Not the smeared diffuse color, but very specific one. So the radiation is emitted or absorbed when changing orbits. The radiation is absorbed when it goes up a level, emitted when it comes down a level. You get a photon of very specific frequency. Okay? So that leads to the quantum theory of the atom. Okay? And this is Bohr's theory. And he started with the simplest atom, the hydrogen atom, and it worked like a charm. Okay? When you got to the higher level, you couldn't get it to work anymore, but it worked for hydrogen. Okay? Now, much earlier, or somewhat earlier, a guy named Balmer, I can't think of what his full name was, it probably doesn't matter, but he had noticed these and talked about or written about them, and he actually came up with an equation to describe them, okay, and it's called the Balmer series, you know, because of that. He's a Swiss mathematician named J.J. Balmer. Not really that much of a physicist, more of a mathematician, so he came up with an equation that worked, okay, that fit all the visible lines that came out of hydrogen. Unfortunately, they never could do anything beyond hydrogen, but they did get it to work for hydrogen. And this is Bohr's equation. There's Planck's constant displaying the change of energy level, E equal H frequency. The E sub n there describes what energy level you're at, okay? And I'm not going to go in, but these are the Balmer lines, okay? The very basic line is down here at negative 13.6. Higher energy than that, still a negative number, but higher energy is negative 3.4. Now, they don't show anything falling from there, but from level 2 to 6, if something goes from 3 to 2, you get that red, 4.6 times 10 to the 14th hertz, pretty close to what our red was in the previous example. The blue-green is in the range of 6.2 times 10 to the 14th hertz. This violet is 7.9 or 6.9 times 10 to the 14th, but then this higher energy violet is 7.3 times 10 to the 14th. And that's closer to what we used in that previous example. And these were the lines that Balmer wrote equations for. And they worked. Okay? They were empirical equations. He was a good mathematician and made them work. But the physics of it comes more from these. The E sub n, the 2, 3, 4, 5, 6, those are your n's, and the high level minus low level, depending on what level they're falling. Falling from this level to that level, that gives you your HF. And that's how they calculate these frequencies. So it's pretty complicated math, but not too bad. The lowest energy state is called the ground state. The higher energy states are excited states. The photon energy equals the difference in the state energies. The one between this is the red, between that is the blue-green, between that is the lower violet, between the other two is the higher energy violet. Okay? And without going into gross mathematics, let's just sort of leave it like that. You can play with that and see how they get these various frequencies by doing the energy level here, these joules here, and you get those by negative 13.6 divided by n squared, where n is, this is 1, that's 2, 3, 4, 5, 6. That's how you get these numbers, and then the difference between these numbers gives you HF divided by H, and that gives you the frequency. So you can go through that exercise if you want to. It is sort of fun to see how it works. Okay? For right now, just know that the higher states are called the excited states. Okay? Now, that was, okay, I think that's about the point of 8.3. So let's see if we can, let's do 8.3 here. That seems to be the only place that gives us room to do it. Calculate the wavelength of the violet light, N equals 6, in the hydrogen line spectra according to Balmer's equation. So Balmer's equation is this one. Am I still black? I think I am. Or it's not quite black, but close to it. 1 over lambda, lambda is a wavelength, is equal to R. Okay? Now, R, you'll see, is a constant of nature. I think it has a name, but I'm not going to go into that now. No, this is a different one. It's 1.097 times 10 to the 7th per meter. That's just the constant. Okay? R times, and this is Balmer, just a pure mathematical equation, 1 over 2 squared minus 1 over n squared, where n is the energy level here. Okay? N equals 3, 4, 5, and 6. Okay? So it says, calculate the wavelength of the violet, N equals 6. So this will be 1 over lambda is equal to, I'll write down that number, 1.097 times 10 to the 7th. And that is a per meter. Okay? Strange unit. Times 1 over 4, that's 2 squared, minus 1 over n squared. Well, n is, it tells you here, is 6, so this will be 1 over 36. Okay? So this is 1.097 times 10 to the 7th per meter times, okay. To handle your fractions here, let's least common denominator of 36 and multiply this by 9, multiply that by 9, that gives you 36. So 936 minus 136 is 836, which you could reduce to make it 4/18, which would be 2/9. So reduce that, 4 will go into that, 4 will go into that, 2/9. Okay? So, if you got your calculator handy, do 1.097 EE or EXP 7, multiply that by 2/9, multiply by 2, divide by 9. That should give you a number. Okay? And then, that number that you get, does anyone have a number there? Something around 10 to the 6, right? Has anyone done it yet? Then hit the reciprocal key. Now the reciprocal key on some calculators is 1 over x. Some calculators will be x to the minus 1. That key, once you have that number, that you get here, 1.097 EE or EXP7 times 2 divided by 9, that will give you something times 10 to the 6th. Then hit one of these two keys, whatever key you have that does that, and that will give you a lambda. See, this is the reciprocal of lambda. That'll give you a lambda. They say in the text is about 4.11 times 10 to the minus 7th meters. Okay? Because you see, when you reciprocate this, you get meters. Okay? Now, that's a little surprising to me. No, okay, that's right. It's a short wavelength, which is a higher frequency. So, yeah. Okay. I just happened to note that it's really close to 5:45, which is time to do roll again. So let's do that while we're at it. Isaac never made it in today, did he? Okay. He was out Tuesday as well. Ty is still here. Gary's still here. Michael's still here. Dalton never made it in today. Melanie's still... Ooh, did I forget Melanie? No, I'm sorry. Colton's not here today. I'm sorry. I skipped Colton. Melanie's still here. And Stephanie... Did we lose Stephanie?
She didn't come to
Wait a minute. I guess she wasn't here. I don't know why. Got her marked. Okay, Hunter. We lost Hunter, didn't we? Wait, Hunter. Wait a minute. Oh, I had marked Hunter in then Stephanie's place. So he was here, and now he's gone. So he's not here. Tyler hasn't come in yet. He said he'd be late tonight. He had to take someone to a doctor's or something. Okay. Gersain never made it in today. Justin is still here. Trent is kind of here. Okay. Demetric is still here. Jose is still here. Cody didn't make it in today. Patel is still here. Taylor is still here. Peyton is still, no, Peyton's still here? Yeah, I see you. Okay. You're behind Taylor. I couldn't see you. Okay. Chase is still here. Mac is still here. Are you worse? Yeah, there you are. Okay. Okay. Zachary just came back. So you're here. Kevin is mostly here, I guess. Stephen is still here. Spencer didn't make it in today at all, did he? Okay, Brian is still here. Raina hasn't made it in today for a long time. And Sarah's still here. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. That's 3, 5, 10, 12, 14, 16, 17. Okay. Sorry, I had to do a pause there. I should have turned off the recorder. All right, so there was example 8.3, and we did find the lambda of the violet light, which you see across the page, is exactly what they got. They said lambda is 4.1 times 10 to the minus 7. Okay. So, we've already started talking about Bohr's theory. We found out these quantum leaps, okay? We talked about this, the ground state, the excited states. Okay? Now we're ready for, or at least getting close to being ready for the quantum mechanics. That's 8.3. Before we get there, there is one more example, 8.4. So I think we're going to have to go back to our favorite slide there and clear this out of the way and do this one. An electron in a hydrogen atom jumps from the excited energy level n equal 4 down to n equal 2. So we got going from n equal 4 to n equal 2. Excited down to a lower level. What is the frequency of the emitted photon? Okay? Now, what you're required to do here without doing all the math of it is saying, so here's what the theory tells us. HF is equal to E sub 6, high, which are here E sub 4, minus E sub 2. Okay? Now, we're not going to calculate the E's. You could if you wanted to, but they just read them off the chart. So if you go back, or in this case, ahead to these, E equal 4 is, E sub 4 is negative 1.36 times 10 to the minus 19. 1.36 EE or EXP minus 19, that's a negative, minus E2, which is 5.44, negative 5.44 times 10 to the minus 19. Negative 5.44 times 10 to the minus 19. These, by the way, are both in joules. Okay? So this is negative 1.36 times 10 to the minus 19 joules. Minus a minus is plus 5.44 times 10 to the minus 19 joules. And when you do that subtraction, because there are different signs here, you get 4.08, I believe it is, times 10 to the minus 19 joules. Okay? Well, that's F. Go back to pick up what Planck's constant is, and that is, and what we're going to do is divide both sides by H. So this is HF. So let's divide both sides by H. Wipe out the H here. And Planck's constant is 6.63 times 10 to the minus 34 joule second. Okay? Notice the joules cancel out. Okay, so if you got a calculator, know how to do this on your calculator, or phone if you're using your phone. 4.08 EE or EXP negation 19 divided by 6.63 EE or EXP negation 34. Okay? And you'll come up with a frequency of, does anyone have that frequency yet? This is 8.4. I see here in the text is 6.15. Does anyone have that?
Yes.
Okay, 6.15, because it's basically 6 into 40. That's going to be 6 point something another. And then you'll have times 10, or EXP, times 10 to the positive. It's 19 minus, because you moved that up one, made that a, probably, yeah, 14, okay. Made that a 20, and that would make it 14 per second, which is the same as, well, why do I put parentheses there? I don't need that. Which, by the way, a per second is a hertz. So this would be 6.15 times 10 to the 14th hertz. And if you look at your spectrum, that would be 6.15. They have it 6.2 times 10 to the 14th. Your blue-green, somewhere between blue and green. All right. Okay, all that, Bohr's theory, Balmer's theory, spectrum. The bad news is, the sad news is, that Bohr's theory only modeled the line spectrum of hydrogen. They could not figure out a way to get it to go any higher. Even helium, the very next simplest molecule, there's just too many complicating factors in there. They couldn't get it to work. Further experiments established a wave-particle duality of light and matter What in the world is that talking about? Well, there were some people that thought light was always measured in waves. Okay? That's why we use frequency, because what is the distance, or the wavelength is the distance between the peaks of a wave. Okay? And wave and frequency would be how frequently how many of those pass in a second. So that's what we're talking about. So that was the wave nature of light, but Einstein came up and said, no, light has a matter type thing. It comes in little packets of light, which would be more like particles. Okay? So there are actually particles. Well, there was a guy, Young, I can't think of his first name. Let's see if I can find him. Can't see it. Just forget about it and just call him Young. Okay. Young did a two-slit experiment that produced interference patterns for both photons, which is light, which you expected, but also for electrons, which are particles. Okay? And he said, hey, even particulate matter does have wave characteristics, so therefore maybe it's not too surprising that wave type thing, photons, have particle characteristics. So that's why they called it a wave-particle duality for both light and matter. The bigger the matter, the harder it is to find the wave characteristics, and for the smaller the energy type thing, the harder it is to find the matter characteristic. But they both interface there. This is really low-level description of it. And that was beginning to be the birth of quantum mechanics. So let's look at matter waves. There was a French physicist, Louis de Broglie. Now, when I took quantum mechanics, I had it for two quarters when I was an undergraduate, the junior level and senior level. And both times I wound up with this theoretical physicist from Ireland who was writing his own book, and he spent the entire class talking to the board, writing as furiously as he could, and it was a room sort of set up like this that had, I think, a 4 or 5 panel chalkboard that covered the entire wall like this. And he started here, and he wrote top to bottom across the board, went all the way down, in a 50-minute class, went all the way down, filled all 4 boards, started back here, and started again, and got usually about halfway before the 50 minutes were over. He was flying. He was talking with the strongest Irish brogue I've ever heard in my life, and I could hardly understand what he said, and his writing was so fast and furious I could hardly read what he said. He was blocking your view most of the time. It was a nightmare. But I remember in his Irish brogue, this was the Broglie. He really coughed it out there, Louis de Broglie. Okay, I'm sure the French turned over in their graves when they heard his pronunciation of de Broglie. Okay, he postulated these matter waves, even for large type things. The wavelength was related to the momentum of the particle. To have momentum, you have to have mass times velocity. You can't have mass if you're a wave. You have to have mass if you're a particle. So it's related to the momentum. And the matter waves and atoms are standing waves. That was the key to de Broglie's model. And what do we mean by that? Well, first, here is his wavelength related to, which in a sense is equal to the reciprocal of, or proportional to the reciprocal of the momentum. And guess what pops up here? Good old Planck's constant again. Boy, that's all over the place here. This had nothing to do with energy matter. This is wavelength and momentum. And there's Planck's constant is the constant of proportionality. Again, okay? And that's the same Planck's constant as before, 6.63 times 10 to the minus 14 joule seconds. Okay? Amazing that would work in Planck's formula that was talking about a completely different thing is the constant of proportionality here as well. Okay? Now here's what we mean by standing waves. Remember we said that the electron is confined to given orbits, and it only radiates or absorbs when it jumps up or down an orbit. De Broglie said these are not just circular orbits, these are standing wave orbits. There is a wave that does like this. This is what gives the electron its wave characteristic. It must be a, what they call here, a standing wave, and it has to be continuous. You can't have it breaking off and going in all sorts of directions there. That wouldn't work. It has to be a standing wave. Now, it stays in this orbit, but does it in a wave-type nature. And it has to be connected. Okay? In math, they have names for that. I can't think what it is now. Okay. Now, that was the basis of de Broglie's work. Okay? And these are the matter waves. Now, let me go back to, here we have a place that we can do. Example 8.5. What is the wavelength associated with a mass of 0.150 kilogram baseball? That is a pretty big particle, okay? Okay? With a velocity of 50 meters per second. That's probably a pretty good speed. I can't translate that to miles per hour easily in my head, but it's something pretty good speed. Okay? Now, what we just had, I'm going to skip forward a little bit. Here we have it. Okay? The wavelength, lambda, is equal to Planck's constant, 6.63 times 10 to the minus 34 joule second, divided by mass, 0.150 kilograms, velocity, 50.0 meters per second. Now, we have a problem here, Houston, and here's what it is. We need to break down what a joule is. A joule is a kilogram meter squared per second squared. Okay? So the second here wipes out one of those seconds, and then you have a per second up here and a per second down here. They wipe each other out. This meter wipes out one of those meters, okay? And the kilograms wipe out each other, and that leaves you with a wavelength in meters, single meter. Okay? Let's see what it is. Okay, now, I'm going to tell you how I would do this. You can do it however you want. I would do 6.63 EE or EXP, negation 34, divided by 0.15. You don't need to put that extra zero in. And then divide again by 50. Okay? Get equal and see what you get. It's going to be incredibly small. I'm going to write down what the book has, 8.85, or 84, sorry about that, I can't read. Times 10 to the minus 35. We thought Planck's constant was small. This is even smaller. Meter. Okay. That's 884, comma 000, comma 000. I mean, you got something like 11 sets of 3 zeros there. Incredibly small number. Okay. Wait, I said it wrong. 0.0000000. That's 30. I said it wrong. 34 zeros, then 884. So the decimal in front of all that. Incredibly small number. No wonder we don't notice the wave nature of it. The wavelength is so incredibly small you'll never detect that. Okay? Now, let's also do this for an electron. Okay? So we're going to use a lot of the same things here, so let me erase just portions of this. Different mass, but it's going to have a mass. Different velocity, but it will have a velocity. Planck's constant is still there. I wish I hadn't erased what I did. And so this will be different, and this will certainly be different. Okay? So, the mass of a electron, if you go to the front inside cover of the book, electron rest mass 9.11 times 10 to the negative 31 kilograms. Whoops. 9.11 times 10 to the minus 31 kilograms. Did I get it right? Yep. Okay. Now, the electron velocity is 6.00 times 10 to the 6. 6.00 times 10 to the 6 meters per second. Okay? And we'll do the same thing with that. So Planck's constant, 6.63 times 10 to the minus 34 kilogram meter squared per second squared, and one of those cancels out there, divided by 9.11 times 10 to the minus 31 kilograms times 6.00 times 10 to the 6 meters per second. Okay. Now, again, we'll go through the same thing. We're left with a per second up here. That per second cancels that per second. This meter cancels one of those meters. That's a little m in there. It's really small and hard to see. But and the kilograms cancel kilograms, so they go out. And all you got are the numbers, and it'll come out in meters, which is a wavelength. So if you got your calculator, 6.63 EE or EXP, negation 34, that was same as before, divided by 9.11 EE or EXP, negation 31, and divide that answer by 6, EE or EXP 6, and you should get something on the order of
1.21.
second
1.21.
1.21. Let's see. Yep, 1.21 times 10 to the minus 10. Is that what you get?
No.
Meters.
I got 54.
You got what?
58. I don't know how.
Okay. Well, let's just look at exponents for a minute. When you multiply these two together, you add exponents, that's minus 25, and minus 34 minus a minus 25 is going to be a minus 9, but when you do the math here, it's going to move one more decimal, so it'll be minus 7. So that seems right. It can't be 30 or 50 or something. Minus 10 looks right. Okay, so that's the wavelength there. As compared with the wavelength of negative 10 to the minus 35, that's a big difference. So yeah, electrons do have measurable wave characteristics. Definitely measurable wave characteristics. Okay? All right. So let's move on from there to wave mechanics. Okay? Boy, have we hit enough names. This was developed by Erwin Schrödinger. He came up with one big, hairy equation. It's called Schrödinger's wave equation. I'm not about to write it down because I'm not sure I could even reproduce it to any reasonable facsimile, but it's a huge, massive equation. It treats atoms as three-dimensional systems of waves, okay? And you do various things with that, which includes taking partial derivatives and other things like that. So the math is way beyond the nature of this course. It contains successful ideas of the Bohr model, but much more, okay? It describes hydrogen atom, but Bohr's model did that, but also many electron atoms, things that have way more than one electron like hydrogen does. And it forms our fundamental understanding of chemistry. This one equation does that, okay? Now, I'm sorry I can't write it for you, and you wouldn't want me to write it for you. It's a big, hairy-looking mess, okay? They don't even bother writing it in the book, okay? But there's another name. And if you hadn't wound up with a paper topic yet, we've hit how many names? J.J. Thomson, Rutherford, Milligan, Thomson, Einstein, Bohr, Planck, Schrodinger. Okay. We'll hit more. Not that many more, but we will hit more. So here's the quantum mechanics model. Okay? This is on page 216 in your text. The quantum numbers specify electronic quantum states. Okay? Now, they say here's the visualization. It's a pretty poor visualization. Okay? But here's what we got. The wave functions are basically probability distributions, and the electrons are, you can't tell exactly where they are, so that's what they mean. They're delocalized. You can't say where, but you can say more than likely they're about in here. Okay? So if this is a probability distribution of your electrons, you see that if you take just this part, you get basically account for 90% of the electron. The function will indicate they're within there. So we'll count them as there. Somewhere there, but somewhere, yeah. They could be just about anywhere, but we'll say with 90% probability they're somewhere in that sphere. Okay? Now, here are those quantum numbers. And again, they don't do a great job of describing them. I'll try to fill in a little bit. The principal quantum number is called n. Okay? Now we saw the n's in Bohr's model. Same thing here. We saw the n's in Balmer series. Same thing. These are your energy levels. Okay? The primary energy level. It relates to the average distance from the nucleus. So small n is pretty close to the nucleus. The bigger n, on average, is getting slightly further away. Okay? But remember, the electrons could be anywhere. But this gives you statistically where they are. The second quantum number is called the angular momentum quantum number. First is called the principal quantum number, which is the energy level. The second is called L. First is N. The second is L, the angular momentum quantum number. That tells you sort of how they're distributed within that average distance. Okay? And here are the labels for that. S, P, D, F, G, and H. Who came up with these? I'm not sure. Okay? But we're only going to deal with S, P, D, and F. We're not ever going to touch a G or an H. Theoretically, they're out there. All right? The third quantum number is your magnetic quantum number. The second is angular momentum quantum number. The third is your magnetic quantum number. Okay? Now, that is a spatial orientation of the orbit. 2 is spatial distribution. 3 is spatial orientation. How does it orient itself? And then the fourth is the spin quantum number. Those are easy. There's only 2, up and down. They're usually plus 1/2 and minus 1/2. That's all you got for a spin quantum number. Really easy. They don't even give it a letter. Okay? sometimes they give this one of M, but they don't even mention that here. So those are the 4 quantum numbers. Ooh. Okay, they haven't told us how they got this out of Schrodinger's model, but it does come from there. So here's basically what we're looking at. The principal energy level, 1, 2, 3, 4. Average distance from the nucleus. Okay? The next one, the SPD, this kind of stuff. The s orbital is the innermost orbital somewhere in there. The p orbital is along one of the axes. Okay? This way, or this way. Okay? They show on the x here, you could have that same thing on y or same thing on z. Those are your p orbitals. They don't. Let's see if they're going to show D. I don't think they will. They might. Okay, here's the P. Like I said, one's along the X, one's along the Y, and one's along the Z. They oriented them a little bit differently here. Those are the 3 possibilities for your P. Only one possibility for S, the sphere around there. The P and the P's are like this. Now the D's. Okay, they don't show the D. Sorry. I think they do in the book. By the way, there is a blurb at the top of page 217 on Science and Society Atomic Research. Okay? There are some questions to discuss. You can look at those. You might find the possibility of a paper topic somewhere there. All right. There was the S. These were the 3 different orientations of P. These are the D orientations. Oh, what a mess. Okay? And we're not even going to come close to doing an F. Okay? G and H, just forget about it. We'll never go there. Okay? But each of these there's 5 sets of lobes holding 2 electrons each for a total of 10 electrons. The S, that look like this, can only hold 2 electrons. The P, 2 each in the X, Y, and Z, so a total of 6 electrons. The D, 5 orientations, okay, and 2 times 5 is 2 electrons in each, and that would give you your 10 possible D electrons. F, okay, so this is 1 times 2, 3 times 2, 5 times 2, F is 7 times 2. Odd numbers here, so you could have 14 orientations of your, 5 orientations of your F, 7 orientations of the F, 2 electrons each, so a total of up to 14 electrons there. Okay, now why 2 electrons each? 1 spin up, 1 spin down. That's why I said the spin quantum numbers up or down. That's all you've got, sometimes called plus 1/2 and minus 1/2. We don't have to even worry with that. But the 4th is just gives you guts. It's the easy one. All right. Again, the N, the first one, average distance from the nucleus. The next one is the energy sublevel, and that's the S, P, D, and F. That's within the given energy. And then the magnetic quantum number is next. Okay. Here is a table 8.2. Let me see if... Okay. They mention something here and they just sort of fly by it. They don't show it in the slide. There is a thing called the Heisenberg uncertainty principle. If someone needs a different topic, here's one for you. And there, I didn't see him come in, but I realize he's here. Tyler is here. Okay. All right. Now, no one else has come in, have they? I think I called Zachary when he came in. So, all right. So here's table 8.2. You'll find this at the top of page 218. Your main energy level for n equal 1 only has one subinterval s. The only one that holds 2 electrons. That's all, folks. Energy level, main energy level n equal 1 only has one energy sublevel s and maximum electrons 2, and that's all she wrote. Now, they're going to do this later. I'm going to do it now. Okay? While on the periodic table, look at the first row. Hydrogen here, helium there, that's all you got. That's level 1. They call it period 1, but that's n equal 1. Spin up, spin down, 1s, one sublevel s. That's all you got. 2 electrons in it, and that's all you got. Hydrogen and helium. Okay? Now, on the next energy level, n equal 2, you have s and p. You can increase 1 every time you go up 1. Okay? Well, s can only have 2, p can only have 6, because it has 3 lobes, up to 2 electrons each. This is one lobe, you might say, just that sphere, 2 electrons in it, 3 lobes, 2 in each, so that would be 6. So a total of 8. Looky here. Second energy level, n equal 2, there's s, 1 and 2, p, 1, 2, 3, 4, 5, and 6. You're just showing the periodic table here. This illustrates. Now, periodic table was developed, not quite looking like this, but somewhat similar, by a guy named, a Russian chemist, physicist named Mendeleev, way before quantum mechanics came into being. He sort of set it up this way, and then when quantum mechanics came, they explained why it worked that way. It's really amazing how science ties together such. Now, n equal 3, it has s, p, and d, but notice n equal 3 only has s and p. And there's a reason for that. We're going to get to it later. N equal 4 can have up to 4 levels, s, p, d, and f. And by the way, remember, s, 1 times 2 is 2, p, 3 times 2 is 6, d, 5 times 2 is 10, f, 7 times 2 is 14. Okay? So that's how you get there. So n equal 3 can have up to 18 electrons in the main energy level. Okay? And n equal 4 can have up to 32. You notice they don't on the periodic table, and there's a reason for that. And we're going to get to that next. How are we doing on time? Okay. Kinda. Yeah, I think we're doing all right. Okay. So here's our electron configuration. This is 8.4 in your text, page 218. The arrangements of the electrons you arrange electrons into these atomic orbitals. Now, principal quantum number was n. That's your first quantum level. Angular momentum 2, magnetic quantum number, specified orbital. Okay? And then these electron configurations specifies the atom's quantum state. Here's another name for you. I think it's Linus, but let me make sure of that. Pauli. Yeah. No, Wolfgang Pauli. I'm thinking Linus. There's another name that's similar to Pauli, but that's a different person. Okay. Wolfgang Pauli, Austrian physicist. And he came up with this exclusion principle. And what that says is that each electron has a unique quantum number. If n is equal to 1, you only have 2 electrons. It's 1s1 and 1s2. That's all, folks. Okay? In level 2, you have 2s1 and 2s2. Then you have 2p1, 2p2, 2p3. Yeah, you just increase them that way. Okay? So each one has a unique quantum number. Maximum of 2 electrons per orbital Spin up, spin down, plus 1/2, minus 1/2, whatever you want to call it. The chemical properties are determined by that electronic structure. And what that means for us is that all the things that live in this row that have that one S1 electron, or the S1 electrons in them, they all act the same chemically. So lithium and sodium and potassium all act pretty much the same. Beryllium, magnesium, calcium, strontium, they act the same. These transition elements here, they act the same. These act the same. All the ones in the columns here act what? All these fluorines, chlorines, fluorines, iodine, guess what? They all are one electron short of having a filled shell. Okay? These over here in number 8, they all act the same. They don't react with anybody because they have no unpaired electrons. They don't want any more. They don't want to lose any. So they don't react with anything. Okay? So the chemical properties are determined by that electron structure. Okay? Now, how do we write these configurations so we get them all down? The electrons fill available orbitals in order of increasing energy. And this is why the third column doesn't still have but 8 elements in it. Okay? And here's what's going on there. The shell capacities, we've already said, S can only hold 2, P6, D10, F12. Now, you can have a few of them, but that's the max. Okay? So they're going to show us an example with strontium. And if you want to find strontium on the periodic table, it's right over here. I actually may have said it. It's underneath calcium. It's over here, number 38. And level 5, so N is equal to 5, and it's still an S electron here, and it's S2 because it's the second column here. So that's where we're going to go for it. Now, here is the way they do it. Now, this is a bit bizarre, but it works like a charm. Okay? You fill the 1S first. Okay? Then when you filled it, you have to go back, and what they did, they left off this because it makes it really confusing. But from 1S, then you go around here and go to 2S. From 2S, you go up here and go to 2P. From 3S, you go up here and go to 3P. From 4S, you go up here and go to 3D. 5S, you go and you follow this pattern all the way. This indicates the energy level, even though, okay, they left off some, so you can't do it there. You don't need that. Everything will be covered before you ever get there. Okay? So, strontium is 38 electrons. So let's start. 1S, 2 electrons. That's 2. Then you go up here and get 2S, 2 more electrons. That's 4. Go up here to 2P, 6 more electrons. That's 10. 3S, 2 more. That's 12. Go up here to 3P, 6 more. That's 18. 2 more make 20. Okay? Go up here. The D's have up to 10. 5 times 2 is 10. So now you're up to 30. And 2 more. Wait a minute. Yeah, okay. 6 more makes 36. And 2 more makes 38. That's where we stop. 5S2. 5S2 is right where strontium is. 5S2. There we are. So that's how you fill up the periodic table, by following this pattern. This is why you fill up 1S first, then 2S, and then 2P, then 3S and 3P. Not 3D yet, because you have to do 4S before you get to 3D, and that's where this group comes in. Those are the Ds. There's 10 of them there. And then when you get to the Fs, way down here, that's these here. They go in these places right here. It's called the lanthanum series and the actinide series. Those are 14 that go in there. You can't do the table, stretch it out, so they just put them at the bottom of the page. And that fills up more than enough. We We go up to 118 here. Some of these are not even named. Okay, that's how you fill up your periodic table. That's your writing the electron configurations. Okay, that's how you do it, and you use this. Use it. We'll use it in lab on Tuesday. Okay, and here's how you write it: 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2. Stop there. That gets you exactly to 38. That's the electron configuration for strontium. Oh, what a joy, huh? Now, no energy-wise, of course, 1's less than 2, 2's greater than 1, 2p is greater than 2s, 3s is greater than this, 3p is greater than that, 4s is greater than that, but 3d is greater than 4s. That's where it gets a little squirrely, but that's why you follow this zigzag pattern. That fills it for you just right. Then 3p, then 6, and 5s2. From there, you would go on to 4d10. You know, you keep on going that way. I'm sorry, yeah, 4d10. All right. All right. So, what are our periodic chemical properties? I've already hinted on this. This is understood in terms of electron configuration. Okay? The electrons in the outer orbits determine the chemical properties. That's the key. Summarized in the periodic table. And here's the thing. I already pointed this out to you. The rows correspond to the periods. Okay? That's why we call it periodic table. N equal 1 is the first row. N equal 2 is the second row. N equal 3. Now, they get a little squirrely because after 3 you get in 4s you followed by 3d, so you're sort of out of order in your primary principal quantum number, but you still see the general idea. That first column now, the columns of the families or groups, in the first column are called the alkali metals. That's where sodium lives. Remember I talked about it? Highly, highly, highly reactive. Okay? That's why you can't even let it touch water. If you were to touch pure sodium, you'd get a burn immediately. Why? Because it interacts with the water from your skin. Okay? It's amazing. Number 2 is the alkaline earth. That's where strontium was. That's second column. Magnesium, calcium are in there. Okay? Beryllium's in there. Okay? Jump over to 7. Those are the halogens. Those are the fluorines, chlorines, iodines, bromines, those kind of things. They have almost a filled shell. Okay? Let's go back. The alkali metals, 1 electron in the outer shell. Just 1. They are real easy to lose that because then they'd have a filled outer shell. It would have everything in it. They're unbalanced. They're an ion now, but they're happy with that because they like to have a filled shell. The alkaline earths have 2 in the outer shell. They don't mind losing those 2. That's why magnesium and calcium make a lot of ionic compounds. The halogens way over there have 7 in the outer shell. They want to have 8. They want it so badly, they'll steal electrons like crazy. They're crooks, okay? And they will get an electron. They become negatively charged. That's why sodium will lose 1, chlorine will gain 1, form sodium chloride, and they're happy campers. Both of them have filled outer shells, but they come together because this one's positive, that one's negative. They have an electronic bond, and they won't break. I mean, those are really strong. So the halogens have missing 1 electron from having a filled outer shell, so they steal electrons like crazy. The noble gases over there in 8, that's the helium, neon, argon, xenon, krypton, radon, they're all over there. They have filled outer shells. They don't combine with anything. Yes?
Krypton, a real gas.
Krypton is, yeah. Yeah, you thought it was the Kryptonite was what Superman used, right? Yeah. No, they use that name. It's a real gas. And by the way, notice all these? They're all gases. Even radon with an atomic mass of 222. That should be a solid. But they don't combine with anything, not even with each other. They're gases. Radon.
Gas in your house.
Yeah, and you can get it, yeah, it comes up through the soil. That's what makes it so dangerous, is that it moves through anything, okay? It doesn't combine with anything, okay? Now, the A group are the families, that is the ones we've been talking about. Okay, here. 1A, 2A, don't do the B's, those are transitions. 3A, 4A, 5A, 6A, 7A, and 8A. That's what we're talking about here. Those are the A group family. The main groups are representative elements. The B group are called transition elements or metals. And that's where you find manganese, chromium, iron, cobalt, nickel. We talked about those in the last chapter. Carbon, zinc, silver, gold, mercury, osmium, iridium. All these things. Platinum, somewhere there's platinum. They're all the metals. They're transition metals. Now, what's characteristic of them, their electrons sort of float, and they go wherever they want to. These stay really fixed near there. The A's stay really fixed near theirs. The B's kind of float. That's what makes them transitions or metals. That's what makes them great conductors of electricity, great conductors of heat, whereas a lot of the A groups are not either of those. All right, here's the periodic table. 1A, 1S1, 1S2. 1S1, 1S2, 2S1, 1S1 and 1S2, 2S2, 1S3. You have to repeat all the others to fill up every one of those electrons. But the electrons, this is the atomic number, which is the number of protons. To be balanced electrons, that's the number of electrons as well. Remember that. So 4, so 1S1, 1S2, 2S1, 2S2. You only write one. You write this 1S2, 2S2. This one you'd write 1S2, 2S1. Okay? Because the upper number is what adds. And then you go on like that. Here are the approximate atomic weights. That's from averaging your isotopes together. That's exactly what it says. 1, S, 1 and 2, 2, S, 1 and 2, 2, always have to stop and think, yeah, P, 1, 2, 3, 4, 5, 6, 3, S, 1 and 2, 4, 3, P, 1, 2, 3, 4, 5, and 6, 4, S1, S2, then you come in with the 3, D1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, and then you get to 4, P, 1, 2, 3, 4, 5, and 6. So that's where that zigzagging does in the table. And the same thing here, but when you get down here to 1, 2, 3, 4, 5, 6, S1 and 2, then you go over to the 4, F, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 13, 14, then this one starts your, I can't remember which number that is, 5D, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, and then your 6, P, 1, 2, 3, 4, 5, and 6. So it gets all crazy, but that's from that looping that we did back on the earlier thing. But that's where these come into play then. These are the F's, these are the S's, these are the P's, these are the D's, and these are the F's. And you follow that zigzag route to get there. Now, how are we doing? We're okay. All right. Okay. Now, maybe it's going to show that. I think they will. All right, it's a little bizarre they put this in here now, but they do. They're only showing here the electron dot notation, they call it, for your S's and your P's. Not your D's and your F's. Those are transitions. Okay? The 1s1 has just one dot there. The 1s2 has two. That's a filled shell. Helium's a noble gas. It doesn't combine with anything. Then you do 2s1 and 2s2. And then your two P1, P2, P3, P4. But you count all these two. You leave the S's in here. And this is D1, D2, D3, D4, D5, P, 1, 2, 3, 4, 5, and 6. Okay? When you get the neon fill outer shell. So you see they're counting the S's in with these, and you try to get a configuration of 8. So you go through that the whole way. This is real easy to lose these single electrons and even the double electrons. Real easy to steal a single electron, sometimes stealing 2 electrons here. Well, a lot of these, as you get more of these and these in here, they start sharing electrons, not exchanging them, sharing them. And when they either lose or gain, you call that the bonding is electronic bonding, because it's electrostatic bonding, positive attracted to a negative. When they share, you call it a covalent bonding. You share the electrons, so they're co-value, same value for either. But don't worry about that yet. Okay. I think there's another slide here. Yes. Okay. Now.
So glad I broke those things.
Say that again.
I said that.
You need it longer?
No, sir.
Oh, okay. Here's the other thing they said. They say here the 1, 2, and 3 outer electrons, these, they say, lose to become positive ions, and these are called metals. They're usually called soft metals, but they are metals. Okay? Like I said, sodium is a soft metal. Now, the 1s are easiest to lose. The 2 will lose, but they're a little harder. The 3s will lose, but they aren't quite as strong as these are. Okay? The 5, 6, and 7, those are these, under these, 5, 6, and 7, they tend to gain electrons to form negative ions. Well, especially the 7s, a little less so the 6s, and really very weakly the 5s. Okay? These are all nonmetals over there, pretty much anyway. And then you have the semiconductors, which basically form a band that goes down kind of like, starting with silicon here, and goes down like this. Now the next slide I'm going to show you will show this a little bit better. But they mention them here. Here's where they show them here. Everything over here now, here's with one exception. Hydrogen is not a metal, okay? Not quite a metal. Actually, in I think it's in the sun. Those who had my Physical Science 111 course, remember they called it metallic hydrogen? And I said that's a strange name for it. In that sense, hydrogen acts like a metal. And sometimes it's at very cold temperatures and sometimes it's very hot. So they put it here. Really, sometimes they group hydrogen over here because it's one shy or one extra, okay? But all these are metals. These are called your soft metals. These are called your transition metals. And then these metals angle down this way. Your nonmetals are these here. They angle down this way, like this. These are your noble gases. They don't combine with anything, okay? But these are called nonmetals. Certainly the gases will be nonmetals, but you classify those as noble gases. They're completely separate. The things in between here are what they call the semiconductors. They have metallic-like properties, but then non-metallic-like properties. So these are great conductors. These are non-conductors. Here are your semiconductors. So if you were wondering where they came from, the periodic table, they were there all along, but people just didn't understand them. Okay? Now we use them like crazy in our electronics. Okay? So that's the metals, the non-metals, and the semiconductors. Metals are usually good conductors, non-metals usually lousy conductors, semiconductors something in between. Now, one sort of little exception here, carbon can be a pretty good conductor if it's graphite carbon. If it's diamond carbon, it's a total non-conductor. So carbon, depending on its internal configuration, it can go either way, kind of. Oh my goodness, is that the end of the chapter? Okay. They didn't show on the slide set a couple of pretty important slides. One is table 8.3, which shows your electron configuration. So if I go back a few slides, here it is. The electron configuration. It shows them for your first 20 elements. That's hydrogen through calcium. There's your electron configuration right there. Here's the table that we used here. I put in the swirly little lines there. There's a firework configuration, they say here. Some of the, for instance, strontium, the one we were talking about on this slide, it makes one of the really bright lights when you're doing flares and fireworks. Okay? Another table they didn't include are tables 8.4 and 8.5. These are your electron structures for the alkali metal family. That's the first column. These right here. The alkali metal, lithium, sodium, potassium, rubidium, cesium, and francium. Don't mess with these too much, mostly those up there. They go through francium, in fact, francium. Then they do electron configuration for the category 8, fluorine, and these are called the, the noble gases. Okay, those are the ones I was talking about. Helium, neon, argon, krypton, xenon, radon. Okay. There is a blurb on the top of page 222, the rare earths. That's what we call these down here. Okay? These are rare. They don't show up in large quantities. They're always solids in the earth. And these are increasingly important in some of the newer technology. And one of the countries on the earth that has the biggest concentration of these is the Congo in Africa. Probably per area is probably one of the richest countries in the world as far as having minerals, incredible minerals there.
Where?
The Congo.
Where?
It's in the center of Africa.
What country is it? I missed it.
It's the Democratic Republic of Congo. Okay? Big country right there. You know, where Africa has the armpit here, it's right below the armpit coming in there. But it's one of the poorest countries in the world. It has been exploited. It was originally a colony of Belgium. It used to be called the Belgian Congo. And King Leopold of Belgium, pardon the phrase, he raped that country like crazy. He abused the people. He tried to steal as much of the minerals as he could. He did. He was awful. Okay? He left it in shatters. It didn't know how to govern itself, anything else. It did break away and become an independent country, and it's been...
And the politicians did something.
Yeah, and then their own politicians, they don't know how to govern, and it's really sad. So guess what? Guess who's the biggest friends to the Congolese people now? The Chinese. They're in there ripping off as many of the minerals as they can so they can get their technology ahead of ours. And they're doing a great job of it. They really are true businessmen. Don't have much, I hate to say this, moral leaning. They do whatever it is that's going to make them money. to be a communist country, they're great capitalists in some sense. Okay, but anyway, there's the rare earths. There's another blurb, and this is the one I was talking about. Dmitry Ivanovich Mendeleev, 1834 to 1907. So he was in his waning years at the time quantum mechanics came into being that were ultimately going to explain his periodic table. Okay, I don't think he ever lived to see it, but it came awfully close. There's a person behind the science. There's a closer look at semiconductors. You can certainly take a look at that. Metals and charge, that's sort of interesting. The outer orbitals, you can take a look at that. And you'll hear me say this every chapter. Nothing replaces reading the chapter. I've flown through this chapter giving cursory descriptions. Read the chapter, you'll get a lot better feel for what's going on. It's deep, and they tried not to get too deep, but it's pretty. The summary is amazingly short for such a complicated chapter. The summary of equations are not too long either, only 5 of them. The key terms are relatively short, but they're pretty important ones. They list them alphabetically, but they give the page number where they're first located or identified. Then applying the concepts, 49 questions, that's about average, with answers. Best thing to study for the test. Questions for thought, there's only 12 of those, fewer than most chapters for such a complicated chapter. That's sort of surprising. 6 for further analysis, that's about normal, maybe a few more than normal. The parallel exercises are basically like your examples we did in class, so if you want to do some of those, you certainly can. Especially those that they say, dealing with the electron configurations, okay? Wish we had time, for example, for chapter 9. That's really, we got you to the crest of that, but we can't take you over the line. We just don't have time. So with that in mind, that pretty much does it. Any questions on chapter 8? That was fast and furious. It will get loaded. Maybe you'll get loaded. I don't know. I didn't say that. Okay. But I'll put it out there on YouTube so you can go back and review what I said. Read the book to review what it does. So on Tuesday, for those who came in a little late, on Tuesday we'll, number 1, have pizza. Starting at 3:15. I'm going to have 9 pizzas here, 3 cheese, 3 pepperonis, and 3 sausage. If that sounds okay with y'all. Okay? Then I'll be passing out all the labs and tests. So if you haven't finished the lab, haven't taken a test, you've got until Tuesday at 3:15 to get it done. After that, too late, folks. Too late. Okay? While y'all are eating pizza, I'll be passing out the labs and the tests. And then once we get all those out, we'll do the lab for chapter 8, the one we just did today. It's strictly a paper lab. We'll do it here in this classroom, and you'll do various things that we talked about in class today. Okay? Then after that, you can go home if you like, or, no, actually, since we finished chapter 8 today, the last 30 minutes of the class, after we have pizza, pass out the things, do the lab, when you finish that, you can take your test on chapter 8. Okay? It's not going to take a lot of time to do all that. Probably less than 2 hours. Okay? So if you want to, this is completely up to you. If you want to take your final early, you can do that. Okay? Anytime after we finish the chapter 8 test. You have to do the chapter 8 test before I'll give you the final though. Okay? If you want to wait till Thursday to do the final, I'll be here. Come on in Thursday and we'll do the final. Okay? And that's all we got scheduled for Thursday. If you want to take it early, you can take it after you finish your chapter 8 test. Right. Okay? And then that'll wind it up. So folks, please do your student course evaluations. If you want to wait till you see that final grade, you can, but don't forget to do them. Okay? Don't forget to do them. Are any of you graduating this term? You are. So you, okay, for you, oh my goodness, you have to be here you have to take your final, the test and the final, before. Can you do it sometime Monday or tomorrow? Okay, either one. I'll be here. I'm not going to Birmingham campus for the rest of this term for office hours because I don't have an office. B building is still closed. So I'll be here tomorrow. If you want to come do them tomorrow, you can. If you want to do them anytime Monday, but I have to have your grades in by noon. Come for pizza at 3:15, but you don't have to do anything else. And you can do your lab if you want to tomorrow or Monday too. I don't have it made out, or I give it to you right now. If you want to hang around after class, I'll give it to you. Okay? All right. I have it made out. I don't have it run off. I have it made out. Okay. Any questions? Chapter 8 or the whole term? Do you want to take your Chapter 6 test now, or you want to study a little, work on your formula equation sheet, or whatever? It's 15 minutes, 20 minutes early, but I'll give it to you now if you want it. Okay. All right. Let me do this real quickly.